Welcome to our deep dive into one-planar graphs.
It's a fascinating area.
Yeah, so we've got a few papers to look at. The first one is called Basis Number of One-Planar Graphs.
Okay.
So, and this is from 2018 by some folks from, mostly from, I guess, Czech Republic.
Yeah, Brno.
Yeah, Brno, and one from Spain.
Okay.
So let's jump in. So I guess like the starting point here is like, what is the basis number of a graph?
Right.
You know, what is that?
So maybe just one step back. What is the cycle space of a graph?
Okay.
So the cycle space of a graph is a vector space where every element is like a set of cycles. And you can think of every cycle in a graph as a vector, and you can add these cycles together.
Right.
And when you add them, you take what's called a symmetric difference. So you only keep the edges that appear an odd number of times.
Right.
And the zero element is the empty set.
Okay.
And so the cycle space is this vector space of all these different cycles.
Right.
And we know that we can generate this whole vector space by Eulerian subgraphs, which are subgraphs where every vertex has even degree.
Right.
So if you think of a graph like just a square,
Right.
that square is a cycle, and every vertex has degree 2. So that's an Eulerian subgraph, and that would be a basis element for the cycle space of a square.
Right.
But in general, you'll have larger graphs
Right.
that need more cycles to generate their cycle space.
Okay.
And that's where the basis number comes in.
Yeah. So what is that?
So the basis number of a graph,
Mm-hmm.
denoted by like a little b of g,
Yeah.
is the smallest k,
Right.
such that there exists a k basis.
Okay.
And a k basis is a set of Eulerian subgraphs
Right.
that generates the whole cycle space.
Mm-hmm.
And every edge appears in at most k of these subgraphs.
Oh, so that's where the k comes from.
That's where the k comes from.
Okay. So that's like the number of times you can use an edge in a particular.
Exactly, in a particular Eulerian subgraph.
Got it.
And
so that's like the basis number.
that's the basis number. So if you think of like the example of a square, the basis number is 1.
Right.
Because you only need one cycle to generate the whole cycle space.
Right. You just need that square.
You just need that square.
Got it. And is there like a way to sort of visualize, like, you know, what a basis is for like a more complex graph?
Yeah. So you can think of it like maybe like a cube.
Uh-huh.
Right. So a cube has 6 faces.
Yeah.
And each of those faces is a cycle.
Right.
And so you could have a basis for the cycle space of a cube that's just those 6 faces.
Okay.
But you could also have other sets of cycles that generate the same cycle space.
Okay.
And so the basis number would be the smallest number of cycles that you need to generate that whole space.
Got it. And so how does this connect to planar graphs?
So that's where MacLane's planarity criterion comes in.
Okay.
MacLane was a mathematician who proved that a graph is planar if and only if its basis number is at most 2.
Oh, okay.
So planar meaning you can draw the graph on a plane without any edges crossing. And so this was kind of a surprising result that this algebraic property of the basis number is equivalent to this geometric property of being able to draw the graph without edges crossing.
Wow. That's pretty wild.
Yeah.
So that's really neat. And so, you know, I guess the next step then is to say, okay, well, you know, what about these one planar graphs?
Right.
Which are, you know, almost planar, you know, they allow for just one crossing per edge.
Exactly.
And so like, is there, you know, something similar
Right.
to MacLane's planarity criterion for one planar graphs?
That's a great question. And that's actually what this paper is all about.
Okay.
So you might think that since one planar graphs are so close to planar graphs,
Yeah.
they might also have a small basis number.
Yeah, you would think, right?
Yeah.
Yeah.
But it turns out that that's not true.
Okay.
The basis number of one planar graphs can be unbounded.
Really?
So for any number you can think of,
Yeah.
there's a one planar graph with a basis at least that big.
Wow. So that one little rule change of just allowing that one crossing really just blows everything out of the water.
It changes everything. Yeah.
Huh. That's fascinating.
So like even though they seem very close to planar graphs,
Right.
in this sense, they're very far away.
Oh, that's so interesting. Okay, so like how do they show that?
So they construct these one planar graphs with unbounded basis number.
Yep.
And the way they do it is they start with a graph that has a large basis number.
Okay.
And we know that such graphs exist.
Right.
And then they make sure that the maximum degree of that graph is 3.
Okay.
And the way they do that is if they have a vertex with degree larger than 3,
Yeah.
they just kind of replace it with like a little tree
Got it.
that kind of redistributes the connections.
Okay.
And then the final step is they want to get rid of any multiple crossings.
Right, because that would violate the one planarity.
Exactly. So they just subdivide the edges by adding new vertices.
Right. Okay, so you're just sort of like,
Stretching it out.
yeah, stretching it out and making sure that there's only one crossing per edge.
Exactly. And so this way they can construct one planar graphs with arbitrarily large basis number.
Wow. So, given like a graph with, some basis number k,
Yeah.
can you always sort of do this transformation to make it one planar?
Yeah. So as long as you can make sure the degree is at most 3,
Right.
and that you can always do.
Right.
You can always kind of stretch out the graph to get rid of those multiple crossings.
Got it. Okay, so it seems like these one planar graphs,
Yeah.
they can be pretty wild.
Yeah.
What about like independent crossing one planar graphs?
Right.
So these are like a subclass.
Yeah. So those are called IC planar graphs for short.
Okay.
And those are one planar graphs where no two crossings share a vertex.
Okay.
So it's like you're trying to impose some order on the crossings.
Right.
But even within this subset, the basis number can still be unbounded.
Oh, really?
Yeah.
So even that like extra restriction
Yeah.
of not allowing them to share vertices isn't enough?
Exactly.
Or bring it back down. Wow. Okay. So it seems like, a lot of the work in this area then is focusing on different subclasses.
Yeah.
To see like, okay, where can we actually like get a bound on the basis number?
Exactly.
Okay, cool. So before we like dive into all those different subclasses, I guess it's worth just kind of like defining all these terms.
Right.
Because there's a lot of them.
Yeah.
Okay, so like one of the things we've already been talking about is, uncrossed edges.
Right.
So like what is that formally?
Formally, an uncrossed edge is just an edge that doesn't have any crossings in the drawing.
Right.
And then you can have an uncrossed graph,
Mhm.
which is just a graph where all the edges are uncrossed.
Okay.
And then the skeleton of a one planar graph,
Yeah.
denoted by scup G,
Yeah.
is the maximal subgraph of G that contains all the uncrossed edges.
Okay, so it's like the biggest
Yeah.
like planar subgraph you
It's
can find in there.
Yeah.
Okay.
And then we have this idea of skirt walks. So if you imagine you're standing at a crossing in a one planar graph,
Right.
you're surrounded by 4 regions.
Yeah.
And each of those regions is bounded by a walk along the edges of the graph.
Right.
And that walk is called a skirt walk. So it's like a walk that goes around the crossing without actually using the crossing itself.
Okay.
And then a poppy
Yeah.
is a special structure in a one planar graph
Okay.
where the union of the 4 skirt walks
Yeah.
around a crossing forms a simple cycle.
Okay.
And that cycle only uses edges from the skeleton.
Okay.
And so if all the crossings in a one planar graph form poppies, then we call that a poppy one planar graph.
Okay.
And then there's also full crossing one planar graphs.
Right.
And those are one planar graphs where the 4 vertices around a crossing
Yeah.
form a K4 subgraph,
Okay.
which is like a complete graph on 4 vertices.
Oh.
And that K4 is also drawn close to the crossing itself.
Okay, so it's like the crossing is kind of like embedded in a K4.
Exactly.
Okay.
And then optimal one planar graphs are just one planar graphs with the maximum possible number of edges.
Okay.
And so that forces all the cells to be triangles
right.
with one crossing.
Right, because otherwise you can add another edge in there.
Exactly.
Okay, got it.
And then near independent crossing planar graphs.
Okay.
Or NIC planar graphs. Are one planar graphs where no 2 crossings share 2 endpoints.
Oh, so the crossings are kind of like spread out.
Yeah, they're a little bit more independent.
Okay.
And so those are some of the key definitions.
Okay, so, one of the things that comes up a lot in this paper is this idea of the skeleton.
Yeah.
So, what is it about the skeleton that makes it so important?
So the skeleton is kind of like the underlying planar structure of the graph.
Okay.
And so if the skeleton is connected,
Yeah.
then it turns out that the basis number of the graph is at most 4. And this is true for both locally maximal one planar graphs and poppy one planar graphs.
Okay, so I'm remembering now that a locally maximal one planar graph is...
Yeah, so a locally maximal one planar graph is one where you can't add any more edges
Right.
without violating the one planarity condition.
Right, so you've squeezed as many edges in there as you can.
Exactly.
Got it.
And so if the skeleton of such a graph is connected, then the basis number is at most 4.
Okay, and is that true for any one planar graph with a connected skeleton?
Not necessarily.
Okay.
So it's specifically for locally maximal one planar graphs
Okay.
and poppy one planar graphs.
Got it.
And the reason why it's true is because you can essentially divide the graph into 2 planar subgraphs.
Okay.
And each of those subgraphs has a 2 basis thanks to Maclane's criterion.
Right.
And the connected skeleton kind of ensures that these two subgraphs overlap in the right way.
Okay.
So that you can combine their bases
Yeah.
and get a basis for the whole graph.
Okay.
And since each of those subgraphs has a 2 bases,
Yeah.
the whole graph has at most a 4 basis.
Got it. Okay, that's pretty neat.
Yeah, so that's kind of a key result for one-planar graphs with connected skeletons.
Okay, so we've talked about like this sort of general case
Yeah.
of one planar graphs with a connected skeleton having a basis number of at most 4.
Mm-hmm.
But we've also said that there are some subclasses where the basis number is even smaller,
Right.
like those full crossing one planar graphs.
Yeah.
So like, how does that work?
So full crossing one-planar graphs actually have a basis number of at most 3.
Okay.
And the way you find a 3 basis for such a graph is you first orient the edges of the skeleton.
Okay.
And you want to do this in a way that each 4 cycle surrounding a crossing has 2 edges going clockwise and 2 edges going counterclockwise.
Okay, so you're like balancing it out.
Exactly.
For the crossing.
Yeah.
Okay.
And then once you have this orientation,
Mhm.
you can construct these special bases for each K4 poppy. And you can combine these poppy bases with a basis of the skeleton.
Yeah.
But you have to exclude the cycles around the crossings.
Right.
And so if you do this carefully,
Mhm.
you can make sure that no edge is used in more than 3 of these Eulerian subgraphs.
Oh, okay, so that's like where the 3 comes from.
Exactly.
Is that it?
And so this gives you a 3 basis for the whole graph.
Okay, so it's like you're taking advantage of that structure of those K4 poppies
Yeah.
to kind of like get that lower basis number.
Exactly.
Okay, that's pretty cool.
Yeah. So that's kind of a key result for full crossing one-planar graphs.
Okay, and so what about those poppy one planar graphs that aren't full crossing?
Right. So they can also have a basis number of at most 3,
Okay.
but only if they have this thing called a balanced orientation of their skirt walks.
Okay.
And so a balanced orientation is just a way of directing the skirt walks,
Okay.
such that for any crossing,
Mhm.
exactly, 2 skirt walks go clockwise and 2 skirt walks go counterclockwise. And so this balanced orientation is kind of crucial
Yeah.
for getting that 3 basis.
Okay.
And then there's also this idea of near independent skirt walks,
Right?
which is similar to the idea of near independent crossing graphs.
Yeah.
But now we're focusing on the skirt walks. And so if a poppy one-planar graph has near independent skirt walks,
Yeah.
then it automatically has a balanced orientation.
Okay.
And so that means it has a basis number of at most 3.
Okay, so it's like a sufficient condition.
Exactly.
Got it. That's cool.
Yeah. So those are kind of some of the key results
Okay.
for poppy one-planar graphs.
So we've seen that, these full crossing one planar graphs
Yeah.
have a basis number of at most 3.
Right.
And these poppy one planar graphs with balanced orientation or near independent skirt walks also have a basis number of at most 3.
Exactly.
So it seems like 3 is kind of like a magic number here.
It does seem that way. Yeah.
Yeah. But it makes me wonder, like, what about the one planar graphs that don't fit into these categories?
Right.
Like, what's the smallest one planar graph that doesn't have a 3 basis?
So that's a great question.
Yeah.
And it's actually still an open problem.
Really?
Yeah.
Wow.
So we've looked at a lot of candidates,
Mm-hmm.
even graphs like the Desargues graph, which isn't even toroidal.
Right.
And they all seem to have a 3 basis.
Wow.
But the smallest one we found with basis number at least 4
Yeah.
is this modified version of the Toot 8 cage.
Okay.
Which has 34 vertices.
Okay, so that's our current, like, lower bound?
Yeah, exactly.
Wow, that's interesting.
Yeah, so the search continues.
Okay, so it's possible that there's, like, a smaller one out there
Yeah.
that we just haven't found yet.
Exactly.
Wow, okay,
Yeah.
so, like, how do they even come up with this modified 2-day cage?
So the Toot 8 cage is this really cool graph.
Okay.
It's a cubic graph.
Okay, so every vertex has degree 3.
Every vertex has degree 3. And it's the smallest cubic cage with girth 8.
Oh, okay, so can you remind me what girth is again?
Yeah, so girth is just the length of the shortest cycle in the graph.
Okay.
So in the 2-day cage, the smallest cycle has 8 edges.
Okay.
And so to create this modified version,
Yeah.
we do some specific operations to it.
Okay.
The details are a bit technical,
Okay.
but the main idea is to subdivide some edges and add new vertices.
Okay.
And we do this in a way that preserves the one-planarity of the graph,
Okay.
but also increases the basis number.
Okay, so you're like stretching it out.
Yeah, exactly.
But in a very specific way.
In a very specific way.
Got it.
And so this modified version of the Toot cage is our current best candidate
Okay.
for the smallest one-planar graph without a 3 basis.
That's really cool.
It's pretty fascinating.
So it seems like there's like a lot of open questions here.
Yeah, definitely.
Like, can we actually drop this balanced orientation requirement for Poppy1 planar graphs? Like, is it possible that they all have a 3 basis?
Yeah, that's a great question.
Could there be a locally maximal one planar graph with a basis number of 4?
Yeah, so that's another open question.
And then there's also this question of complexity.
Right.
Like, what's the complexity of computing the basis number?
Yeah, so that's a really important question.
Yeah, for general graphs and for one planar graphs specifically.
Exactly.
And then there's also the question of testing.
Yeah.
Like, is it easy to test if a one planar graph has a basis number of 3?
Right, so all these questions are still open.
Wow.
Yeah.
So there's a lot of work to be done.
There's a lot of work to be done, yeah.
Wow, that's exciting.
Yeah, it's a really active area of research.
Okay, cool. So this paper is kind of giving us like a really nice overview of like the state of the art.
Mm-hmm.
And it seems like, even though these one planar graphs are like, seemingly very close to planar graphs,
right,
they're actually like very different.
Yeah.
When it comes to this basis number.
Exactly.
Okay, cool. So maybe we can move on to the next paper.
Sounds good.
Which is called Basis Number and Local Graph Operations.
Okay.
And this one is also from 2018.
Okay.
But it's by a different group of authors.
Okay.
And so this paper kind of focuses on analyzing how like local changes to a graph affect its basis number.
Right.
So like what are some of the key ideas in this paper?
So one of the key ideas is that you can actually subdivide an edge without changing the basis number at all.
Oh, really?
Yeah. So subdividing an edge just means inserting a new vertex along that edge.
Okay.
And so if you do that,
the
basis number stays the same.
Interesting.
Yeah. And that's kind of like a really useful tool for proving things about basis number.
Got it. And
then another key idea is that if you add an edge to a graph, you can increase the basis number by at most 1.
Oh.
So that's another really important result. And then there's also edge contraction. And contracting an edge can never increase the basis number.
Okay, so it can either stay the same or go down.
Exactly.
Okay.
And so these 3 operations, subdividing an edge, adding an edge, and contracting an edge, are kind of like the basic building blocks for understanding how local changes affect the basis number.
Got it.
And so this paper kind of explores these operations in detail.
Okay.
And proves some really interesting results about them.
So like what kind of results?
So for example, they proved this lemma that says if you have a graph that can be obtained from a planar graph by adding at most k edges, then the basis number of that graph is at most 2 plus k.
Oh, okay. So it's like you're starting with that planar graph, which we know has a basis number of at most 2.
Right.
And then for every edge you add,
you're
just increasing that bound by 1.
Exactly.
Okay, so that's like a nice simple.
It's a nice simple bound.
Yeah. Okay, cool.
Yeah.
And so are there any like open problems?
Yeah, so there are a few open problems in this area.
Okay.
One of them is whether there exists a constant c such that removing an edge from any graph G increases the basis number by at most c.
Okay.
So we know that removing an edge can increase the basis number, but we don't know by how much.
Okay.
And so this open problem is asking whether there's like a universal constant.
Yeah, like a global bound.
Exactly.
Right.
And so that's a really interesting question.
Yeah.
And then another open problem is whether there exists a constant c such that contracting an edge in any graph G decreases the basis number by at most c.
Okay.
So we know that contracting an edge can decrease the basis number, but again, we don't know by how much.
Okay.
And so these are just a couple of the open problems in this area.
Okay, cool. So, this paper's kind of focusing on, these local operations.
Yeah. But I'm curious, like you mentioned this idea of like charges of edges in a basis.
Right.
And I don't really understand what that means.
Yeah, so the charge of an edge is essentially a way of counting how many times that edge appears in the basis.
Okay.
And the way you define it is you first choose an orientation of the graph.
Okay.
And then for each edge, you look at all the cycles that contain that edge.
Okay.
And you count how many of those cycles go in the same direction as the orientation.
Oh, okay.
And so that number is the charge of the edge.
Okay. And so how does this help us understand the basis number?
So the basis number is just the maximum charge of any edge in the graph.
Got it.
So if you can compute the charges of all the edges, then you automatically know the basis number.
Okay. So it's like a way of...
Yeah, it's like a shortcut.
A shortcut, yeah.
Okay, that's cool.
And so this idea of charges is really useful for proving things about basis number. And it's also used in a lot of algorithms for computing basis number.
Okay, cool. So that's really interesting.
Yeah.
So it seems like, there's a lot of connections between like these different concepts.
Yeah, definitely.
And, maybe we can explore some of those connections in more detail.
That sounds good.
But I think for now we should probably take a break.
Okay.
And we'll come back and talk about some more specific examples.
Sounds good.
Okay.
All right.
Okay. So welcome back to our deep dive into one-planar graphs. And we're talking about basis numbers.
Right.
And I guess we left off talking about charges.
Yeah, charges of edges.
Yeah. And so, like, what are some other ways that charges are used in this area?
So charges are also used to prove some other results about basis number.
Okay.
Like, for example, there's this theorem that says that if you have a graph G and you orient its edges, and then you look at the set of all cycles whose total charge is even, then that set of cycles
is a subspace of the cycle space.
Oh, that's cool.
Yeah. So that's like a kind of surprising result that you can actually use charges to define a subspace of the cycle space.
Okay, so I guess, like, what is a subspace of a cycle space?
Yeah, so a subspace of a vector space is just a subset.
Okay.
That's also a vector space.
Right.
And so in this case, the subspace of the cycle space is the set of all cycles.
Yeah.
That can be written as a linear combination of cycles whose total charge is even.
Got it.
And so that's a really useful result because it tells us that if we want to find a basis for the cycle space, we can actually restrict our attention to this subspace of cycles with even total charge.
Yeah, that makes sense.
Yeah.
And so, like, how does this theorem help us understand basis number?
So it doesn't directly tell us anything about the basis number, but it does give us a tool for studying the cycle space.
And so by understanding the cycle space better, we can hopefully learn more about basis number.
Okay, so it's like a stepping stone.
Exactly.
Okay, that makes sense.
Yeah.
Okay, so I'm curious, like, are there any other theorems or results?
Yeah, so there are a lot of other results about basis number.
Okay.
And a lot of them use charges.
Okay.
But we don't have time to go into all of them here.
That's fair.
But I would encourage you to check out the literature if you're interested in learning more.
Yeah, for sure.
There's a lot of really cool stuff out there.
Okay, cool.
Yeah.
So I guess we've talked a lot about, like, the theoretical side of basis number.
Right.
But I'm wondering, like, what about the algorithmic side?
Yeah.
Like, how do we actually compute the basis number of a graph?
So that's a great question.
Yeah.
And it turns out that computing the basis number is actually NP hard.
Oh, wow. So, like, what does that mean?
So NP hard means that it's unlikely that there exists an efficient algorithm for computing the basis number.
Right.
And so in practice, we often have to resort to heuristics.
Okay, so, like, what are some examples of heuristics?
So one example of a heuristic is to just greedily choose cycles until you can generate the whole cycle space.
Okay.
And so that might not give you the optimal basis number.
Right.
But it might give you a pretty good approximation.
Okay, that makes sense.
Yeah.
Okay, so it seems like, this is like a really active area of research.
Yeah, definitely.
And there's still a lot that we don't know.
There's a lot that we don't know, yeah.
Okay, cool. Well, I think that's a good place to stop for now.
Okay.
And we'll come back and wrap things up in the next part.
Sounds good.
Okay. All right, so welcome back to our deep dive on one-planar graphs and basis numbers.
Okay.
So I guess we've covered a lot of ground.
Yeah.
And I think we're ready to kind of wrap things up.
Okay.
So I guess one of the things that I'm still kind of wondering about is, we've talked about all these different subclasses of one-planar graphs. And we've seen that, like, for some of them we can get a bound on the basis number.
Right.
But for others we can't.
Right.
And so, like, I'm wondering, like, is there any kind of, like, unifying theme here?
That's a great question.
Yeah.
And I think, like, one of the key takeaways from all this research is that one-planar graphs are just really complicated.
Yeah, that seems to be the theme.
Yeah.
Yeah.
Like, even though they're, like, very close to planar graphs in terms of, like, the number of crossings,
Yeah.
they're actually, like, very far away
Yeah.
in terms of, like, their basis number.
Right.
And so, like, I think that's kind of, like, the big surprise.
Yeah.
And it just shows that, like, you know, even, like, small changes to the definition of a graph can have, like, really big consequences.
For sure.
And so I think, like, that's kind of, like, the main message that I would take away from all this.
Okay, and so, like, you know, given that these one-planar graphs are so complicated,
Yeah.
like, what are some directions for future research?
So I think, like, one of the big open questions is, you know, what is the smallest one-planar graph that doesn't have a 3 basis?
Yeah, we talked about that.
Yeah. And so, like, you know, that's something that people are still actively working on.
Okay.
And I think, like, another interesting direction is, you know, trying to understand, like, what other properties of one-planar graphs are related to their basis number.
Yeah, that makes sense.
And so, like, you know, maybe there's some other, like, structural properties that we can identify that would help us to, like, better understand the basis number.
Right.
And so, like, I think those are just a couple of, like, the many open questions in this area.
Cool.
Yeah.
Well, I think this has been a really fascinating deep dive.
Yeah, I agree.
And I've learned a lot.
Me too.
So thanks for joining me.
Yeah, thanks for having me.
Okay. All right. All right, so we're diving into these one-planar graphs and their basis numbers. Got a whole stack of research here, ready to unpack it all. It's about describing loops, but I think it's going to get complicated.
Definitely. Even one edge crossing makes one-planar graphs way more complex than just planar ones.
Yeah. Quick recap. One planar, basically you can draw it flat, some edges cross, but only once each. Cycle space is all the different closed loops you can trace.
Right. And for basis number, we need to describe these loops with minimal instructions. Imagine giving directions to draw them all. Basis number is how many times you reuse an edge.
Makes sense. Low basis number, the graph cycles are simple to describe. Higher number, more complex. Eulerian subgraphs keep popping up. Can you remind us what those are?
Sure. It's a part of the graph. A path enters and exits each vertex the same number of times. Walk back to where you start, visiting every point an even number of times.
So every loop is an Eulerian subgraph, but not every Eulerian subgraph is a simple loop.
Exactly. You could have 2 separate loops not touching, that's still Eulerian. Now, combining them to make new ones, that's where symmetric difference comes in.
Yeah. Rings a bell, but I'm fuzzy on the details.
Okay, imagine drawing 2 Eulerian subgraphs, A and B, on top of each other. Symmetric difference is like erasing the overlaps. You keep edges only in one subgraph, not both. Exclusive OR for graphs.
Okay, starting to see it. So symmetric differences let you get all the loops.
Exactly. This leads to a basis for the cycle space, like building blocks to make all the Eulerian subgraphs and therefore all the loops.
So finding a basis is like the most efficient loop instructions. Basis number tells us how much repetition is needed. Planar graphs have a basis number at most 2, right? But what about when it's one planar, just one crossing? Does that change things?
You'd think almost planar means the basis number stays small. But surprise, you can make one planar graphs with any basis number. It gets complex fast with that one crossing.
Wow, that's counterintuitive. So how do you even construct one with a high basis number?
Theorem 4.1 shows us how. You start with a graph that already has a high basis number. Then you make sure each vertex has at most 3 edges. Finally, you turn it into a one-planar graph by subdividing edges, basically splitting them with extra vertices.
So you stretch it to make it one planar, but keep the high basis number. Neat. Shows how small changes make a big difference.
Exactly. Challenges the idea that close to planar equals well-behaved basis number. Let's explore some one-planar graphs that are more predictable.
Sounds good. Where do we begin?
Well, one interesting subclass is all about the graph's skeleton, the subgraph with all the non-crossing edges.
Okay, stripping away the crossings, looking at the backbone. What about the basis number of those with connected skeletons?
Proposition 4.4 says if the skeleton's connected, so you can travel between any 2 vertices without lifting your pencil, then the basis number is at most 4. They prove it by cleverly dividing the graph into 2 planar subgraphs, using what we know about planar graphs and merging the bases back together.
So even with lots of crossings, that connected skeleton keeps things in check. Interesting. Any particular types of one-planar graphs with connected skeletons we can look at?
There are two mentioned, locally maximal and poppy one-planar graphs. Both always have connected skeletons, which means a basis number of at most 4.
Okay, break those down for us. What do locally maximal and poppy even mean here?
Locally maximal means around every crossing, you've got a complete graph with 4 vertices, a K4, like each crossing has its own little clique of 4 connected vertices.
Okay, I can picture that. What about poppy graphs? What makes them unique?
Poppy one-planar graphs have a cycle in their skeleton around each crossing point, creating a sort of petal structure, hence the name poppy. The Peterson graph is a classic example.
Got it. Both locally maximal and poppy one-planar graphs have this connected skeleton, limiting their basis number to at most 4. But can we go lower? Are there any with even smaller basis numbers?
Yes, there are. Let's talk about one-planar graphs with full crossings. This means that the cycle around each crossing is drawn right next to it, forming a K4, kind of like in locally maximal graphs.
Okay, each crossing is embraced by a 4-vertex graph. What does that tell us about the basis number?
Theorem 4.11 says that for any full crossing one-planar graph, the basis number is at most 3. They prove it by giving directions and weights to edges based on how they're oriented around the crossings. Then they can pick basis cycles so no edge is used more than 3 times in the instructions for making all the loops.
Fascinating. So how the crossings are arranged actually helps limit the basis number.
Right. And get this, optimal one-planar graphs, the ones with the most edges for a given number of vertices, are always full crossing. So they also have a basis number of at most 3, as corollary 4.12 states.
Okay, so full crossing graphs, even the optimal ones, have a basis number of at most 3. What about poppy graphs? Anything special about their basis numbers?
They do. Theorem 4.16 says poppy one-planar graphs also have a basis number at most 3 if they have a balanced orientation for their skirt walks.
Hold on, skirt walks. You've got me curious. What are those?
Imagine walking along the edges of a cell in a one-planar graph. You're basically going around the boundary of a face, but not the crossing point itself. That's a skirt walk. A balanced orientation means assigning directions to these walks so that for each crossing, 2 go clockwise and 2 go counterclockwise.
Like a balanced flow around each crossing. Why is this balanced orientation important for the basis number?
If you can find it, you're guaranteed a basis number at most 3. But here's the thing. Not every poppy one-planar graph has one.
There's the catch. Any example of one that doesn't?
The Peterson graph we talked about earlier, the classic poppy graph, can't be oriented in a balanced way. Figure 10 in the research shows this. How do we know if it has a balanced orientation? And can we still say anything about the basis number if it doesn't?
Good questions. Even within poppy graphs, there's nuance to figure out. It's like we're peeling back layers of complexity with each new type of graph.
Exactly. And even though not all poppy graphs have balanced orientations, there are results for a specific kind.
Okay, tell us about them. What's the special type? What about its basis number?
It's those with near-independent skirt walks. Basically, no 2 skirt walks from different crossings share 2 vertices.
So they're isolated, minimal overlap. Why does this matter for basis number?
Because of this independence, you can orient the skirt walks around each crossing separately. Guarantees a balanced orientation, so basis numbers at most 3. Theorem 4.18 proves this.
I get it. Even without a globally balanced orientation, you can achieve balance locally, enough for a basis number of at most 3. Clever.
Indeed. Let's shift gears a bit. Table 1 in the research lists different one-planar graphs and their properties. What stands out to you?
It's interesting that most of these graphs have a basis number of 3, even though they're one-planar. Hewitt graph, McGee graph, even the Zarg graph. Wait, that one's non-toroidal, right? What was that again?
Non-toroidal means you can't draw it on a donut without edges crossing. It's relevant because all toroidal graphs have a 3 basis. That's a recent result.
So if toroidal graphs have a basis number of 3 and the Dazar graph isn't toroidal, you expect a higher basis number? No.
Exactly. But even the Desargues graph has a 3 basis. That's proposition 4.20. Shows how tricky basis numbers are. They don't always follow what you'd expect.
Right. Always surprises with one-planar graphs. This table has a bunch with basis number 3, but we know from theorem 4.1 some can be much higher. Makes you wonder, what's the smallest one-planar graph that doesn't have a basis number of 3?
Open problem 4.19. It's a big question. We haven't found a one-planar graph smaller than the one in proposition 4.21 with a basis number bigger than 3.
Okay, tell me about this graph. What's so special about it?
It's got 34 vertices, basis number at least 4, and it comes from the Toot 8-cage graph. That's a 3 regular graph with girth 8.
Hold up, let's unpack that. What do 3 regular and girth 8 even mean?
3 regular means every vertex has 3 edges connected to it. Girth is the length of the shortest cycle. So the 2 to 8 cage, shortest cycle, is length 8, but it's still 3 regular. It's balancing complexity and regularity.
I like that analogy. What's this got to do with basis number?
Any 3 regular graph with a 3 basis has to have a girth of at most 7. So the 2 to 8 cage with girth 8 has to have a basis number at least 4.
So the girth limits how low the basis number can go. Makes sense. They took the 2 to 8 cage with its high basis number and modified it to be one planar, keeping the basis number high.
Precisely. But there's a twist. This one planar graph isn't Poppy one planar. We don't know if you can make it Poppy without changing the basis number. This is open problem 4.22. Is there even a Poppy one planar graph with basis number 4? It's like a mythical graph.
So much for those well-behaved Poppy graphs. What about locally maximal graphs? We know they have a basis number of at most 4, but do they actually all have a 3 basis?
That's open problem 4.23. There's a good candidate, shown in figure 6b, constructed using multiple copies of K8, which is a complete graph with 8 vertices, but they remove a perfect matching.
Perfect matching. Explain that.
A perfect matching is a set of edges. Each vertex connects to exactly one other vertex, no overlaps. They remove some specific edges from the K8 graphs to make this locally maximal one planar graph. They think it has a basis number of 4, but proving it is tricky.
It seems like with all these specific types, there are still tons of open questions about basis numbers. It's amazing how one simple concept can lead to such deep mathematical mysteries.
I agree. These open problems really highlight how much we still don't understand about crossings, connectivity, and the basis number. Like, we're just scratching the surface.
To recap, we've gone through different kinds of one-planar graphs: connected skeletons, Poppy graphs, locally maximal graphs, little things like how crossings are arranged, or whether balanced orientations exist. They all affect the basis number. Even with these insights, there are still so many open questions, hints that there might be even more complex stuff hidden within one-planar graphs.
That's right. This whole dive into one-planar graphs has really only been the beginning. What if we let there be more crossings per edge, 2 crossings, 3, even more? Does the basis number become totally unpredictable, or are there hidden structures waiting to be found in those graphs with more crossings?
Now that's a fascinating question. It feels like we're about to step off the map and into uncharted territory, ready to explore those wilder basis numbers.
Absolutely. Let's dive in.
So we've been looking at one-planar graphs, 1 crossing per edge. But what if we change that rule? What if we allow 2 crossings, or 3, or even more? Does the basis number just go wild?
It's a good question, and there's still so much we don't know. Moving beyond one planarity makes things way more complex, that's for sure. Even with 2 planar graphs, 2 crossings per edge, the basis number can be unbounded.
Wow, so even 1 extra crossing throws everything off. Those nice bounds we saw with some one-planar graphs, they probably don't hold up with more crossings.
You got it. More crossings, more ways those cycles can interact, like adding more dimensions to those loop instructions.
Great analogy. I can picture the paths getting all tangled up. But it makes me wonder, are there any hidden patterns in those densely crossed graphs? Maybe new kinds of bounds we haven't even thought of yet?
It's possible. We might lose those neat one-planar properties, but there could be totally new connections between the crossings, the basis number, and things like connectivity or girth. It's something graph theorists are actively looking into.
So we're exploring uncharted territory, looking for new landmarks in this more complex landscape.
Exactly. And who knows what's out there? Maybe whole new classes of graphs with totally unique basis number behavior.
This is exciting stuff. Feels like we're on the verge of big discoveries. But I have to admit, all this complexity and unboundedness, it's a bit overwhelming. Is there any way to make sense of it all? Any strategies mathematicians are using to tackle these more general graphs?
There are a few approaches. One is to focus on specific properties or constraints, see how they affect the basis number. Like, instead of all L graphs with a certain number of crossings per edge, maybe look at ones with a particular connectivity or girth.
So like taming the wilderness by focusing on specific regions?
Right. By adding constraints, we might find new bounds or relationships in those specific types of graphs. Another approach is to develop new tools for analyzing those basis cycles. Maybe find clever ways to break down complex cycles into simpler ones, or see how they interact with each other.
Sounds like a lot of room for creativity. Not just using old formulas, but finding totally new ways to think about these problems.
Definitely. That's what makes this area of research so exciting. New discoveries all the time, always more to learn.
For our listeners who want to join in this exploration, what advice would you give them? Where should they start?
Pick a class of graphs that interests them. 2 planar graphs, graphs with a limited number of crossings per edge, something like that. Then just experiment. See how the basis number connects to other properties. Look for patterns and bounds.
Great advice. And don't be afraid to ask what-if questions. That's how discoveries happen.
Absolutely. Curiosity is key for any graph theorist.
Well, this deep dive has certainly gotten me curious. It's been a journey, starting with planar graphs, then the surprises of one-planar graphs, and now into the unknowns of even more general graphs. Amazing how one concept, the basis number, can lead to such deep mathematical questions.
Glad you enjoyed it. I hope everyone listening feels inspired to explore this area of math. There's still so much to discover, so many problems to solve.
Definitely. This was just a taste of how basis numbers connect to the structure of graphs, and how a tiny change, like adding one more crossing per edge, can completely change things.
It shows how even in a well-established field like graph theory, there are still huge areas to explore.
So one final thought for everyone. Even in math, there's always more to discover. The more we learn, the more we understand about the world around us.
Well said. That wraps up our deep dive into basis numbers of graphs. Until next time, keep exploring, keep asking questions, and keep diving deep into the world of math.
All right, ready to dive into this paper on the basis number of one planar graphs.
Yeah, it's a fascinating look at how, these slightly messier planar graphs kind of behave when it comes to building paths.
Right, because with regular planar graphs, we have that beautiful result from McLean.
Right.
Where you only need like 2 special cycles to generate all the possible paths.
Exactly. But things get way more tricky when we allow even like a single crossing per edge.
So to dive into this, I think we need to start with like the basics.
Of course.
Right. So remind me about the cycle space of a graph.
Yeah, the cycle space, denoted C of G, is essentially a way to capture all the possible ways.
Yeah.
You can create closed loops or cycles within a graph. More formally, it's the set of all Eulerian subgraphs.
Ah, right. Eulerian subgraphs. Those are the ones where every vertex has an even number of edges connected to it.
Precisely. And the reason we care about Eulerian subgraph is that any Eulerian subgraph can be decomposed into a set of edge disjoint cycles.
Okay, I see the connection now. So the cycle space is all about understanding how these cycles like fit together within the graph.
Exactly. And the basis number then asks, what is the smallest number of cycles we need to be able to combine and create a any y cycle in this graph?
So it's like finding the most fundamental building blocks for all possible paths within the graph.
That's a great way to put it. And with planar graphs, McLean's criterion tells us we only need 2 of these building blocks.
Right.
But this paper dives into how one planar graphs can have a much higher, even unbounded basis number.
Unbounded. Yeah. So there are one planar graphs where no matter how many basic cycles you have, you might still need more to create all possible paths.
That's exactly what they prove.
Wow.
And they explore how even seemingly small changes in the structure of these one planar graphs can drastically affect the basis number.
Okay, so before we get to the paper's specific findings.
Sure.
I think let's just make sure we're all on the same page about some like key definitions. We keep mentioning this basis number, but what exactly does that mean in the context of the cycle space?
You're right. It's worth revisiting. The basis number, denoted by B of G, is the smallest number, K, such that the graph has a K-basis.
All right, so K represents the basis number, but what's a K-basis?
So a K-basis is a specific kind of basis for the cycle space, where every edge of the graph is used in, at most, K cycles of that basis.
Okay.
Imagine you have this set of cycles that can generate any other cycle in the graph. That's your basis. Now, each edge in your graph will be part of some of these basis cycles. The K value tells you the maximum number of basis cycles that any single edge participates in.
Ah, I see. So it's like setting a limit on how much work each edge has to do in our cycle building system.
Exactly. The smaller the K value, the simpler and more efficient our representation of the graph cycles becomes.
Right.
And as you mentioned earlier, for planar graphs, McLean's criterion magically shows us that we can always find a 2 basis, meaning each edge is used in, at most, 2 cycles from our chosen basis.
Right. That's what makes planar graphs so nice to work with.
Right.
But with one planar graphs, as this paper explores, things get a lot more complicated.
Exactly. The paper dives into how even seemingly small variations in one planar graphs can lead to drastically different basis numbers.
Okay, before we jump into the paper's findings, can you remind me about the idea of a generating set?
Of course.
I think that's key to understanding how this basis number works.
Imagine you have a vector space. A generating set is a collection of vectors in that space, such that any other vector in the space can be expressed as a linear combination of the vectors in the generating set.
Okay, so we're talking about building blocks again, but this time it's about building any vector in the space.
Exactly.
By combining these, like, special generating vectors.
Precisely. Now, in the context of the cycle space of a graph, our vectors are the cycles themselves.
Okay.
So a generating set for the cycle space is a collection of cycles that, through symmetric differences,
can create any other cycle in the graph.
Right. Symmetric difference, that's where we combine cycles. But if an edge appears in both cycles being combined, it gets canceled out.
Yeah.
It's kind of like constructive and destructive interference.
That's a great analogy. Now, not all generating sets are created equal.
Right.
A basis is a minimal generating set, meaning you can't remove any cycle from it without losing the ability to generate all the other cycles.
Okay.
It's like a perfectly curated set of cycle building blocks with no redundancies.
So every basis for the cycle space of a given graph will have the same number of cycles.
That's true.
And that number is the basis number of the graph.
Not quite.
Oh.
Every basis will have the same number of cycles.
Right.
That's true. But that number is called the dimension of the cycle space, denoted as dim of C of G. The basis number, B of G, on the other hand, is the smallest k, such that there exists a k basis.
So we could have a graph with a dimension of, say, 5, meaning every basis has 5 cycles. Right.
But it's possible that the basis number is only 3.
Exactly.
Meaning there's a special basis where each edge is part of at most 3 cycles from that basis.
Exactly. You've got it. Right. And the dimension itself has a neat connection to the graph's structure. It's equal to the number of edges in the graph minus the number of vertices plus the number of connected components.
Okay.
Mathematically, it's dim of C of G equals the cardinality of E minus the cardinality of V plus 1.
Okay, I'm making a note of that equation. So the dimension gives us the size of any basis. Well, the basis number tells us the smallest charge we can achieve on the edges when choosing, like, a special basis.
Precisely, and the paper we're diving into explores how this basis number behaves for one-planar graphs.
Right.
Which turns out to be quite different from the well-behaved planar graphs we're used to.
Okay, I think we've laid a solid foundation now. So what's the first, like, big surprise this paper throws at us regarding these one-planar graphs?
Well, the first thing they establish is that the basis number of one-planar graphs can be unbounded. This is a stark contrast to planar graphs, where the basis number is always a nice and tidy 2.
Whoa, unbounded. So that means there are one-planar graphs where no matter how many basic cycles you have in your set, you might still need more to create all possible paths.
Exactly. It highlights just how much more complex these one-planar graphs can be compared to their planar counterparts.
Wow. That's pretty wild.
Yeah.
Can you give us a sense of why these crossings create such a dramatic shift in complexity?
Think of it this way.
Right.
When edges are allowed to cross, we introduce new paths and cycles that simply couldn't exist in a planar graph. These new paths weave in and out of each other, creating intricate dependencies.
Right.
It's like those crossings create knots in the fabric of the graph's structure.
Oh, okay.
And untangling those knots might require a much larger set of basic cycles.
Okay, I'm starting to get a feel for why things get so messy. So how do the authors actually prove that the basis number can be unbounded for these one-planar graphs?
They build their proof on a clever construction that involves taking a graph with a known high basis number and transforming it into a one-planar graph without decreasing the basis number along the way.
So they're starting with something we know is complex.
Right.
And then showing how that complexity carries over into the one-planar world.
Exactly. They actually leverage a previous result by Schmeichel, who demonstrated that for any integer, there exists a graph, let's call it G, with a basis number of at least Hora. Now, this graph G might not be one-planar initially, but the authors cleverly modify it.
So what's the first step in this transformation process? How do they start taming this potentially wild graph G?
Their first move is to deal with any vertices that have a high degree.
Okay.
In graph theory, A vertex's degree is simply the number of edges connected to it. If a vertex in graph G has a degree of 4 or more, they replace it with an edge.
Okay, so they're essentially splitting those high-degree vertices, distributing their connections to the two endpoints of this new edge.
Precisely. And they keep doing this until all the vertices in the graph have a degree of at most 3.
Okay.
This process doesn't increase the basis number because contracting an edge, which is essentially what we're doing when we merge those vertices, can only decrease the basis number, or at the very least keep it the same.
Right, we talked about that earlier. It's like we're simplifying the graph structure without making the cycle space any less complex.
Exactly. Now, even with all vertices having a degree of at most 3, the graph might still not be one planar.
Right.
That's where the next clever trick comes in. Edge subdivision.
Edge subdivision. That's where we insert a new vertex along an existing edge.
Exactly.
Effectively splitting it into two edges.
Yeah.
And crucially, we know that subdividing edges doesn't change the basis number at all.
You got it. So the authors draw this modified graph in the plane, allowing for edge crossings.
Okay.
Then, for any edge that's crossed more than once, they subdivide it, adding new vertices until each edge is crossed at most once. This transformation turns the graph into a one-planar graph without altering the basis number.
That's brilliant. So they've taken that initial graph G, which had a basis number of at least A, and transformed it into a one-planar graph with the same basis number.
Exactly.
It proves that one-planar graphs can have arbitrarily large basis numbers.
Exactly. And they even point out that this resulting graph is an isoplanar graph.
Okay.
Because those subdivision vertices they introduce ensure that no two crossings share an endpoint.
Okay, so even with those restrictions on the crossings, we still can't escape this unbounded basis number situation.
Right.
But the paper doesn't just focus on this like wild, unbounded side of one-planar graphs, right?
You're absolutely right.
They also explore cases where the basis number is actually like well-behaved.
Exactly. And that's where the concept of the skeleton of a one-planar graph comes in.
Okay.
Imagine you have a one-planar graph drawn out on a plane with all its crossings.
Okay.
The skeleton is the subgraph formed by all the edges that don't have any crossings. It's like we're stripping away the messy crossed edges and just looking at the clean planar backbone.
Okay, so the skeleton gives us a simplified view of the graph's underlying structure.
Yeah.
Ignoring those, like, naughty crossings.
Right.
What role does the skeleton play in, like, taming the basis number?
The authors prove a key result. If the skeleton of a one-planar graph is connected, meaning there's a path along uncrossed edges between any two vertices,
right,
then the basis number of the entire one-planar graph is at most 4.
Wow, that's a pretty significant constraint.
Right.
So having a connected skeleton seems to bring some order to the chaos, preventing the basis number from spiraling out of control.
Yeah.
How do they prove that?
Their proof relies on a clever combination of techniques. They use a lemma they developed earlier, which states that if you can cover a graph with two subgraphs whose intersection is connected and contains a spanning tree, then the basis number of the original graph is at most the sum of the basis numbers of the two subgraphs.
Ah, right. It's like we're strategically breaking down the graph into simpler pieces.
Yeah.
And then using those pieces to bound the overall complexity.
Exactly. And in this case, they construct those two special subgraphs by carefully partitioning the crossing edges of the one planar graph. They take all the pairs of edges that form a crossing and assign one edge from each pair to the first subgraph and the other edge to the second subgraph. Both subgraphs also include all the edges of the skeleton.
Okay, so each subgraph gets half of the crossing edges along with the entire skeleton.
Yeah.
This ensures that each subgraph is planar.
Precisely.
Because we've essentially untangled the crossings by splitting those edge pairs.
Precisely. And since the skeleton is connected, by assumption, the intersection of these two subgraphs, which is just the skeleton itself, is also connected and contains a spanning tree. This sets us up perfectly to apply that lemma.
Right. So the lemma tells us that the basis number of the original one-planar graph is at most the sum of the basis numbers.
Exactly.
Of these two planar subgraphs.
Yeah.
And since planar graphs always have a basis number of at most 2, thanks to McLean's criterion, the original one-planar graph must have a basis number of at most 4.
You nailed it. It's a beautifully elegant proof that highlights the power of this subgraph covering technique,
Right.
and the importance of connectivity in shaping the basis number.
This is where it gets really interesting.
Yeah.
What kinds of one-planar graphs have this like magically connected skeleton?
Well, one class of one-planar graphs that always have a connected skeleton are the locally maximal one-planar graphs.
Okay.
In these graphs, every crossing is part of a complete graph on 4 vertices, also known as a K4 subgraph.
Okay, so each crossing is like the center of a little K4 subgraph. Why does that force the skeleton to be connected?
Think about it. Those 4 vertices in the K4 subgraph are connected by uncrossed edges, forming a cycle. And this cycle, being part of the skeleton, links up all the crossings and the rest of the graph, creating a connected backbone.
Ah, so those K4 subgraphs act like little bridges, ensuring that all parts of the skeleton are linked together.
Exactly. And this implies that locally, maximal one-planar graphs have a basis number of at most 4.
Okay.
Another type of one-planar graph that falls under this category is the optimal one-planar graph.
Optimal one-planar graph, those are the ones with the maximum possible number of edges for a given number of vertices.
Precisely.
Right, like the most densely connected one-planar graphs you can get.
Precisely. And since they're a subset of locally maximal one-planar graphs, they inherit that connected skeleton property.
Right.
And therefore also have a basis number of at most 4.
Okay, so we've identified at least 2 families of one-planar graphs.
Yes.
Where the basis number is well-behaved. But I have a feeling the paper doesn't stop there, does it?
You're right. The paper goes on to explore cases where the skeleton might not be connected. And in these cases, things get a bit trickier, but they still manage to find some interesting bounds on the basis number.
So if the skeleton's not connected, we lose that nice guarantee of a basis number of at most 4. What do they do in those cases?
They introduce this clever concept called the auxiliary graph.
Okay.
Imagine you take each connected component of the skeleton, remember those are the separate islands of the skeleton that aren't connected to each other,
right,
and represent each component as a single vertex in a new graph.
Okay.
This new graph is our auxiliary graph.
Okay, so we're collapsing those connected components into single points.
Exactly.
Creating a sort of simplified map of the skeleton structure.
Exactly. Now we look at the crossings in the original one-planar graph for each crossing.
Okay.
If the 2 edges involved in the crossing connect vertices from the same 2 connected components of the skeleton, we add a double edge between the corresponding vertices in our auxiliary graph.
So those double edges in the auxiliary graph represent crossings in the original graph?
Yeah.
That bridge the same 2 islands of the skeleton.
Precisely. Now here's where it gets interesting.
Okay.
They prove that if this auxiliary graph contains 3 edge disjoint spanning trees, then the basis number of the original one-planar graph is at most 8.
Hold on. Edge disjoint spanning trees.
Yes.
That means we have 3 separate standing trees within the auxiliary graph, and none of them share any edges.
Exactly. It's a pretty specific condition, but if it's met, we get this nice bound on the basis number.
Okay.
And the reason this works is that those 3 edge disjoint spanning trees guarantee a certain level of connectivity in the original graph's structure.
Right.
Even though the skeleton itself might not be connected.
So even when the skeleton is like fragmented, if there's enough connectivity between those fragments, as reflected in the auxiliary graph, we could still keep the basis number under control.
Precisely. It highlights once again how crucial connectivity is in shaping the complexity of these graphs.
Okay, I think I'm starting to wrap my head around all of it. We've covered unbounded basis numbers, connected skeletons, auxiliary graphs, and even touched on those Poppy 1 planar graphs.
We've laid a good foundation, and I think it's a good place to pause for now.
Okay.
Next time, we can delve deeper into those Poppy graphs and explore how they hold the key to some surprising results about basis number.
Okay, I'm intrigued. Those Poppy graphs have been lurking in the background, and I'm ready to see how they fit into the bigger picture. Until next time.
Until next time. Welcome back to our deep dive into the basis number of one-planar graphs.
I'm still processing all the insights from our last discussion, like, whoa.
We covered a lot of ground from unbounded basis numbers to those intriguing auxiliary graphs.
Right, and we left off with a bit of a cliffhanger about those Poppy 1 planar graphs.
Yes.
I'm ready to learn more about how they fit into this whole puzzle.
They play a crucial role in the paper's exploration of basis numbers.
Okay.
And they lead to some surprising results.
So let's start with a recap. Remind me what makes these Poppy graphs so special.
Remember in a Poppy 1 planar graph, Each crossing is surrounded by a special cycle called a poppy.
Okay.
This poppy cycle is formed by the 4 skirt walks of that crossing
Right.
all joined together.
Right. The skirt walks are those paths that trace the boundary of the cross cell.
Yeah.
Well, like delicately avoiding the crossing point itself.
Exactly.
And in poppy graphs, those skirt walks form like a complete cycle around each crossing.
Precisely. It's like each crossing has its own little protective bubble, a sort of mini cycle that encapsulates it.
Right.
And this poppy structure turns out to have some interesting implications for the basis number.
Okay, I'm picturing these crossings with their little poppy cycles, like tiny fortresses, guarding against complexity. What's the first insight the paper reveals about poppy graphs and their basis numbers?
Well, one of the most striking results is that any poppy 1 planar graph, assuming its skeleton has a balanced orientation, has a basis number of at most 3.
Wow, that's a pretty strong statement, especially considering that we've seen how wild the basis number can get for general 1 planar graphs.
Yeah.
So this poppy structure, combined with this balanced orientation thing, seems to impose a significant constraint.
You're absolutely right. It highlights how specific structural properties can dramatically influence the complexity of these graphs.
Okay.
Now, before we get too excited about this 3 basis result, we need to unpack what this balanced orientation actually means.
Okay, let's break that down. We've talked about the skeleton of a 1 planar graph, which is the subgraph formed by all the uncrossed edges.
Right.
And we know that a connected skeleton can help tame the basis number.
Yes.
But now we're adding this notion of orientation to the mix.
Yeah.
What exactly does it mean to, like, orient a skeleton?
In graph theory, orienting a graph, or specifically its edges, simply means assigning a direction to each edge, like making them one-way streets. So in the context of a 1 planar graph, orienting the skeleton means choosing a direction for each of those uncrossed edges.
Okay, I'm picturing little arrows on those skeleton edges, dictating which way we can travel along them.
Yeah.
But what makes an orientation, like, balanced in the context of these poppy graphs?
The balance refers to how the orientation affects those skirt walks around each crossing. Remember, each crossing has 4 skirt walks tracing its boundary.
Right.
In a balanced orientation, we want exactly 2 of those skirt walks to be oriented clockwise, and the other 2 to be oriented counterclockwise.
Ah, I see. So it's like creating a balanced flow of traffic around each crossing.
Yeah.
With half the skirt walks going one way.
Exactly.
And half going the other. I can intuitively see how that might, like, help organize things.
Yeah.
But how does this balanced orientation actually lead to that 3 basis result?
That's where the real beauty of the paper's proof lies. They develop a very clever construction process that leverages this balanced orientation to create a 3 basis for the entire poppy 1 planar graph.
Okay.
It involves 3 main steps.
Okay, I'm ready for a mathematical journey. Lead the way.
All right, the first step is to focus on the skeleton of our poppy 1 planar graph, assuming it has this balanced orientation of the skirt walks. Our goal is to create a generating set for the cycle space of just the skeleton.
Right.
Remember, a generating set is a collection of cycles that can be combined to create any other cycle within that subgraph.
Right. We talked about generating sets earlier. It's like finding a set of basic building blocks for all the cycles within the skeleton.
Yeah.
How do we go about finding such a generating set for a planar graph like the skeleton?
Luckily, planar graphs have a neat property that makes this relatively easy.
Okay.
We can use the concept of face boundaries to create a generating set.
Okay.
A face boundary is simply the cycle that encloses each face of the planar graph.
Okay, so for the skeleton, we take all its face boundaries.
Yes.
And that gives us a generating set for its cycle space.
Almost. There's one little catch.
Okay.
We need to exclude the face boundaries that correspond to cycles surrounding the crossings in the original 1 planar graph.
Ah, I see. So we're specifically leaving out those cycles that are part of the poppy structures.
Exactly.
It's like we're setting them aside for, like, special treatment later on.
Precisely. Those poppy cycles will be handled in the next step.
Go.
For now, we have a generating set for the skeleton's cycle space.
Okay.
Consisting of all its face boundaries except for the ones directly encircling those crossing points.
Okay, that makes sense. So what's the next step in this 3 basis construction process? What do we do with those poppy cycles that we set aside?
The second step focuses on those poppy structures surrounding each crossing.
Okay.
Our goal here is to find a basis for the cycle space of each individual poppy.
Okay, so we're breaking down the cycle structure of those little poppy subgraphs?
Yes.
But those poppies are essentially just K4 graphs.
Complete graphs with 4 vertices. Don't we already have, like, well-established methods for finding a basis for K4 graphs?
We do. However, the challenge here is to find a basis with specific properties that align with our overall three-basis goal for the entire graph.
Right.
Remember, we want to limit the charge on each edge,
Right.
which means controlling how many cycles from the basis use that edge.
Right. We don't want any edge getting overworked by being part of too many basis cycles.
Exactly.
So we're looking for a special basis for each poppy that keeps the edge charge low.
Exactly. And the authors prove that we can always find such a basis for any poppy.
Okay.
Specifically, they show that there's a basis where we can assign a charge of 1 to 2 of the skirt walks,
Right.
and a charge of 2 to the other 2 skirt walks.
Okay.
All other edges in the poppy have a charge of at most 3.
Okay, so we're carefully distributing the workload among those skirt walk edges,
Yeah.
giving some of them a lighter load, charge 1, and others a slightly heavier load, charge 2.
And crucially, all other edges within the poppy have a charge of at most 3.
You got it. Now here's where that balanced orientation of the skeleton comes into play.
Okay.
We use that orientation to determine which skirt walks get assigned a charge of 1 and which get a charge of 2.
So the skeleton's orientation, which dictates the direction of those uncrossed edges, guides how we distribute the workload within each poppy's basis.
Precisely.
But I'm still not quite seeing how it all fits together to create this 3 basis for the entire graph.
Yeah.
That's the final step.
The third and final step is where the magic happens. We take the generating set for the skeleton's cycle space, the one that excludes those crossing surrounding cycles,
Right.
and we combine it with the carefully chosen bases we just created for each poppy.
Okay.
This merged set of cycles gives us a generating set for the entire poppy 1 planar graph.
Okay, we're merging those separate pieces, the skeleton's generating set and those poppy bases, into one big set. But why is this new set a 3 basis?
Yeah.
How do we know that each edge in the graph has a charge of at most 3?
That's where the cleverness of the construction and the importance of the balanced orientation become clear.
Okay.
Remember, we excluded those crossing surrounding cycles from the skeleton's generating set.
Right.
This means the only cycles that use those skirt walk edges are the ones from those poppy bases we carefully constructed.
I see. So by excluding those crossing surrounding cycles from the skeleton's generating set, we've isolated the skirt walks to be part of only the poppy bases.
Exactly.
And since we meticulously assigned a charge of either 1 or 2 to those skirt walk edges, based on the balanced orientation, we've ensured they don't contribute too much to the overall chart.
Exactly. The balanced orientation guarantees that those skirt walk edges are used efficiently, preventing their charge from exceeding 3.
Okay.
And all other edges in the graph either belong to the skeleton, meaning they're only used in the skeleton's generating set, or they're internal to the poppy structures, where we also limited their charge to at most 3.
Wow, it's a beautifully orchestrated interplay of concepts. The balanced orientation guides the charge distribution within each poppy's basis, and by strategically excluding those crossing surrounding cycles from the skeleton's generating set, we ensure that the skirt walks don't get overloaded. It all comes together to create this elegant 3 basis for the entire poppy 1 planar graph.
You perfectly summarized it. It's a powerful demonstration of how seemingly simple structural properties, like this balanced orientation, can drastically simplify the representation of a graph's cycle space.
Okay, I'm thoroughly impressed. But this brings up a question. How do we even know if a poppy 1 planar graph has a balanced orientation? Is it possible that some of them just don't?
That's a great question, and it highlights one of the open problems the paper mentions.
Okay.
They don't explicitly provide an efficient algorithm for finding a balanced orientation, and it's not clear whether every poppy 1 planar graph even possesses one.
So there's still a bit of mystery surrounding these balanced orientations and their role in poppy graphs.
Absolutely.
I imagine there's ongoing research trying to answer those questions.
Absolutely. The paper actually points out 2 specific open problems related to this.
Okay.
First, can a poppy 1 planar graph without a balanced orientation have a basis number of 4? In other words, is that balanced orientation essential for achieving that nice 3 basis result?
Right. It's possible that there are other ways to construct a basis with a low charge, even without a balanced orientation.
Exactly.
And what's the second open problem?
The second question focuses on locally maximal one-planar graphs.
Okay.
Remember, those are the ones where each crossing is part of a K4 subgraph.
Right.
The question is, do all locally maximal one-planar graphs that are not full crossing have a basis number of 4?
Okay, so we know that full crossing, locally maximal one-planar graphs where every pair of edges crosses have a basis number of 3. But it's not clear whether that same bound holds for locally maximal graphs that have some edges that don't cross.
Exactly. It highlights how even within specific classes of one-planar graphs, there are still open questions and intriguing possibilities.
Well, this deep dive has definitely given me a new appreciation for the subtle complexities of these seemingly simple graphs.
Yeah.
Those little crossings really shake things up. And understanding how structural properties like connectivity, orientation, and those poppy cycles influence the basis number is fascinating.
I'm glad you're finding it engaging. I think this paper does a fantastic job of showcasing the beauty and depth of graph theory.
Yeah.
And the fact that there's still so many open problems just adds to the excitement.
Okay, I'm ready for another mathematical adventure.
All right.
What other intriguing insights does this paper have in store for us?
In the next part, we'll dive into some specific techniques the paper employs to construct those poppy bases and analyze the basis number under different conditions. They introduce concepts like charge redistribution and near-independent skirt walks, which lead to even more fascinating discoveries.
I'm on the edge of my seat. Until next time.
Until next time.
All right, back for the final leg of our one-planar graph adventure. Last time, we left off with those poppy graphs and their surprising 3-basis result, assuming they have that balanced orientation.
Yeah, it's a remarkable finding. It shows how even small tweaks to a graph structure can significantly impact its complexity.
Right, and we ended with some, intriguing open questions about whether every poppy graph even has a balanced orientation.
Right.
And whether it's truly essential for that low basis number. But before we get lost in those mysteries, I'm kind of curious about the mechanics of the paper's proof.
Yeah.
Like, how do they actually construct those special poppy bases that lead to the 3-basis result?
It's a clever process that involves a few key ideas. First, they introduce this notion of charge redistribution. Remember, charge refers to how many times an edge is used in the cycles of our basis.
Right. It's like measuring how much work each edge is doing in our cycle-building system.
Exactly, and the goal is to keep the charge on each edge as low as possible. Now, in a poppy graph, we have those special skirt walks around each crossing. The authors found a way to, shift charge around within the poppy, moving it between those skirt walks and the other edges.
So they're optimizing the workload within each poppy, making sure no single edge gets overloaded.
Precisely. And the way they do this is by carefully choosing cycles that use those skirt walks and internal poppy edges in specific ways. They prove that for any poppy, you can always find a set of cycles that redistributes the charge so that 2 skirt walks have a charge of 1, 2 have a charge of 2, and all other edges have a charge of at most 3.
Okay, so they're meticulously balancing the charge within each poppy, making sure no edge gets a charge higher than 3. But how does this connect to the overall 3 bases for the whole graph? We're not just dealing with isolated poppies, right?
You're right. We need to consider how those poppies fit into the larger graph structure. And that's where the balanced orientation of the skeleton comes in. Remember, the skeleton is that planar subgraph formed by all the uncrossed edges.
Right, it's like the backbone of the graph holding everything together.
Exactly. Now, when we orient the skeleton, we're assigning a direction to each of those uncrossed edges. And as we discussed before, a balanced orientation means that for each crossing, exactly 2 of its skirt walks are oriented clockwise, while the other 2 are oriented counterclockwise.
So it's like creating a balanced flow of traffic around each crossing, with half the skirt walks going one way and half going the other. But how does this traffic flow connect to those carefully crafted poppy bases?
Here's the key insight. The balanced orientation of the skeleton tells us how to choose those special poppy bases with the redistributed charge. Remember, we assign a charge of 1 to 2 of the skirt walks and a charge of 2 to the other 2. Well, the orientation of the skeleton's edges determines which skirt walks get which charge.
Okay, I'm starting to see the connection. So the skeleton's orientation acts as a guide, telling us how to arrange the cycles within each poppy to achieve that balanced charge distribution.
Precisely. It's a beautiful example of how global structure, the orientation of the skeleton, influences local decisions, the choice of cycles within each poppy.
Okay, but we're still just dealing with those individual poppy bases. How does all of this come together to give us a 3 bases for the entire graph?
Remember, in the last part, we talked about how the authors construct a generating set for the entire Poppy 1 planar graph. They do this by combining two pieces. A generating set for the cycle space of the skeleton, excluding those cycles that directly surround the crossings, and the special Poppy bases we just discussed, one for each crossing.
Right, we're merging those two pieces together to create a set of cycles that can generate any cycle in the whole graph.
Yeah.
But why does this combined set have a charge of at most 3 on every edge? That's the key to having a 3 basis.
That's where all the careful setup pays off. By excluding those crossing surrounding cycles from the skeleton's generating set, we ensure that the only cycles using the skirt walk edges are those from the Poppy bases. And since we meticulously redistributed the charge within each Poppy, ensuring no edge has a charge higher than 3, those skirt walk edges are well behaved.
So the skirt walk edges are only part of those carefully balanced Poppy bases where their charge is limited. What about the other edges in the graph?
Well, any edge that's not a skirt walk is either part of the skeleton, meaning it's only used in the skeleton's generating set, or it's internal to one of the Poppy structures. And we already know that all edges within a Poppy have a charge of at most 3, thanks to that charge redistribution process.
So all the edges in the graph are accounted for, and none of them have a charge higher than 3. It's like a perfectly orchestrated symphony of cycles, with each edge playing its part without getting overwhelmed.
That's a great way to put it. It's a testament to the power of careful construction and the interconnectedness of these seemingly simple graph concepts.
Okay, this whole 3 basis result is blowing my mind.
Yeah.
It really highlights how subtle structural properties, like that balanced orientation, can lead to significant simplifications. But I can't help but wonder about those open problems we touched on earlier. What if a Poppy graph doesn't have a balanced orientation? Is it doomed to have a higher basis number?
That's a great question, and it's one that the authors explicitly leave open for further exploration. It's possible that there are other clever ways to construct a basis with a low charge, even without that balanced orientation. Or maybe there's a deeper connection between the existence of a balanced orientation and the basis number that we haven't uncovered yet.
Right, there could be hidden structures or properties that influence the basis number in ways we don't fully understand yet. It's a reminder that even in a field as seemingly well-defined as graph theory, there's always more to discover.
Absolutely. And the other open problem about those locally maximal one-planar graphs that aren't full crossing also points to the mysteries that still lie ahead. We know that full crossing locally maximal graphs have a basis number of 3, but what about those that have some uncrossed edges? Do those uncrossed edges somehow simplify things, allowing for a lower basis number, or do they introduce new complexities that push the basis number higher?
So many intriguing questions. I'm already eager to dive into more research on this topic and see what new insights have been uncovered since this paper was published.
I share your enthusiasm, and I think this paper does a fantastic job of not only presenting some remarkable findings, but also highlighting the exciting open problems that lie at the frontier of this field. It's a reminder that even within a seemingly simple framework like one-planar graphs, there's a rich tapestry of concepts waiting to be explored.
Well, I feel like my brain has been thoroughly stretched and exercised by this deep dive. From unbounded basis numbers to connected skeletons, auxiliary graphs, and those fascinating Poppy cycles with their balanced orientations, we've covered a lot of ground. And the fact that there are still so many unanswered questions just adds to the allure of this whole topic.
I couldn't agree more. This paper has been a fantastic guide through the intricate world of one-planar graphs, showcasing the beauty, elegance, and sometimes surprising complexity that lies at the heart of graph theory.
A huge thanks to you for navigating us through this mathematical landscape. Until next time.
Always a pleasure to dive into these fascinating topics with you. Keep exploring, and who knows what other mathematical treasures you'll uncover.
Welcome back to the Deep Dive. Today, we're going to be taking a deep dive into the world of one-planar graphs and their basis numbers. Buckle up, because this is going to be a fascinating ride.
Absolutely, yeah. It's a surprisingly intricate area of graph theory with lots of open questions.
Yeah.
And even the seemingly simple things can get pretty complex quickly.
Exactly. So we've got a stack of research papers and notes here, and I have to admit some of this stuff looks pretty intimidating.
Right.
But I'm confident that by the end of this deep dive,
Yeah.
we'll have unpacked the core concepts and maybe even discovered some aha moments along the way.
Definitely. And remember, we're talking to you, our listener, directly. So if anything's unclear or if you have a burning question, just imagine you're right here with us, chiming into the conversation.
Okay, let's set the stage first.
Sure.
For anyone who might need a quick refresher, a planar graph is one you can draw on a flat surface without any of the edges crossing.
Yeah.
Think of it like a perfectly laid out subway map.
Exactly. And a one-planar graph is almost like that, except we allow one crossing per edge.
Okay.
It's like the map maker got a little bit lazy, but not too much.
Okay, got it.
Yeah.
So we're dealing with graphs that are almost planar, but with a little bit of controlled chaos.
Right.
Now, where does this basis number thing come in?
Well, the basis number is all about understanding the cycle space of a graph.
Okay.
It's a way to measure how intertwined the cycles in a graph are.
Okay, break that down for me. What exactly is the cycle space?
Think of it like this. Imagine you're tracing paths on the graph that start and end at the same vertex.
Mm-hmm.
We call these closed paths cycles.
Right.
Now, the cycle space is basically the set of all possible cycles you can draw on that graph.
So it's like the graph's fingerprint made up of all these different loops and swirls.
That's a great way to visualize it. Now, the basis number comes in when we try to find a minimal set of cycles that can be combined to generate any other cycle in the graph.
Right.
Think of it like a set of basic building blocks for cycles.
I'm starting to see the connection here. So a smaller basis number means the graph is, in a way, more efficient with its cycles.
Exactly. It means you can create a wider variety of cycles using a smaller set of fundamental cycles.
Okay, that makes sense. Now, the real question we're trying to unravel in this deep dive is whether these one-planar graphs, being so close to planar graphs in structure, also have limited basis numbers, or can they become really large?
That's the million-dollar question. And to kick things off, we're going to dive right into a theorem that kind of throws a wrench into things.
Bring it on. I love a good plot twist.
Well, this one's called Schmeichel's theorem.
Okay.
It basically says that for any number you can think of, no matter how big, there's a graph out there with a basis number at least that big.
Wow.
So in other words, the basis number can be unbounded.
Wait, so that means even if a graph is almost planar, its basis number can still be huge. It's kind of surprising.
It is. And what makes it even more interesting is that we can actually modify any graph to make it one planar and with a maximum degree of 3 without messing with its basis number.
Hold on, how do we do that?
It's all about clever graph transformations. First, we use vertex splitting to reduce the degree.
Okay.
It's like taking a busy intersection and turning it into a roundabout.
Okay.
Instead of one vertex with lots of connections, we create multiple vertices with fewer connections, but still preserving the overall structure of the graph.
Okay, so we're kind of spreading things out to make it less congested.
Exactly. And to make sure it stays one planar, we use edge subdivision.
Right.
Imagine taking a highway and adding some pit stops along the way.
Okay.
This creates new edges and vertices, which helps us reduce the number of crossings.
Got it. So we're strategically tweaking the graph to fit our needs without sacrificing its fundamental cycle structure.
Exactly. Now, while the basis number can be unbounded in general, we do find some limitations when we look at specific types of one-planar graphs. One subclass we're going to focus on is locally maximal one-planar graphs.
Okay, new terminology alert. What does locally maximal mean in this context?
Imagine zooming in on a crossing in the graph.
Okay.
In a locally maximal one-planar graph, every crossing must be part of a K4 subgraph.
Okay.
That's a complete graph with 4 vertices, meaning every vertex is connected to every other vertex within that subgraph.
So it's like every crossing has its own little clique, a tightly knit group of 4 points all connected to each other?
Precisely. Now, another interesting subclass is poppy one-planar graphs.
Okay.
This is where the name gets kind of fun. Imagine each crossing in the graph as the center of a flower, with the surrounding cycle acting as its petals.
Poppy one planar. I like the imagery. So in these graphs, each crossing is at the heart of a little flower-like structure.
You got it. And within this flower, the cycle around each crossing is actually the graph's skeleton.
Okay.
Which is the subgraph made up of all the uncrossed edges. Now, if that cycle surrounding each crossing happens to be a K4, then we call it a full crossing one-planar graph.
Okay, so full crossing one-planar graphs are a subset of poppy one-planar graphs, where the flower is always a specific type, the K4. Got it.
Exactly. Now here's a fascinating finding. One-planar graphs with connected skeletons have a basis number of at most 4.
Okay, hold on. How does having a connected skeleton limit the basis number?
It all comes down to being able to break the graph into smaller, more manageable pieces.
Okay.
Remember how one-planar graphs allow for one crossing per edge?
Right.
Well, if the skeleton is connected, we can cleverly separate those crossing edges to create two subgraphs that are each planar.
So by splitting the one planar graph at its crossing points, we end up with two nicely behaved planar graphs.
Exactly. And since planar graphs have well-defined properties, we can use that knowledge to understand the basis number of the original one planar graph.
That's clever. Now, I'm curious about those full crossing one planar graphs.
Yeah.
You mentioned earlier that we can actually construct a 3 basis for them.
Okay. Yes. It's pretty neat how it works. Remember how we can assign directions to edges in a graph?
Right.
We call that orienting the edges.
Yeah.
Well, by carefully choosing a direction for each edge in the skeleton of a full crossing one planar graph, we can make sure that each edge is used at most 3 times in the basis.
Okay, I'm trying to picture this. It's like we're directing traffic flow in our K4 roundabouts to keep the overall congestion or basis number low.
That's a great analogy. We're essentially optimizing the flow of cycles within each K4 to ensure a smooth ride for the entire graph.
This is getting really interesting. So we've got these full crossing one planar graphs with their K4 roundabouts and their carefully directed traffic flow.
Right.
What about poppy one planar graphs in general? Can we apply similar logic there?
We can, but it gets a bit more complex.
Okay.
Instead of focusing on the entire K4, we need to think about the paths that skirt around each crossing, tracing the boundaries of the cells adjacent to it.
Okay.
We call these paths skirt walks.
Skirt walks?
Yeah.
It's like we're taking a scenic road around each crossing.
Yeah.
So what's the trick with these skirt walks?
The key is to find a balanced orientation for them.
Okay.
This means that for each crossing, 2 skirt walks should be going clockwise and 2 should be going counterclockwise.
Ah, okay. We're back to that traffic analogy.
Yeah.
Ensuring a balanced flow around each crossing.
Exactly. And it turns out that if these skirt walks are near independent, meaning no 2 skirt walks from different crossings share 2 vertices,
Okay.
then we can always find this balanced orientation, which in turn guarantees a 3 basis.
So near independence leads to balanced orientation, which leads to a 3 basis.
Right.
It's a chain reaction of good news for those poppy one planar graphs. But what about those graphs where we can't find a balanced orientation? Does that mean their basis numbers are doomed to be greater than 3?
That's a great question, and it's one that mathematicians are still trying to answer definitively.
Right.
For instance, the Peterson graph, when drawn in a specific poppy one planar way, doesn't have a balanced orientation because of how some of its skirt walks are interconnected.
So it's like a domino effect where the orientation of one skirt walk forces the orientation of the next and so on.
Yeah.
Ultimately leading to an imbalance.
You got it. Now, this doesn't necessarily mean the Peterson graph can't ever have a balanced orientation. Maybe it can if we draw it differently.
Right.
But for this specific drawing, it's a no-go.
So the existence of a balanced orientation might depend on how the graph is drawn.
That's really interesting.
Yeah.
So have we found any poppy one planar graphs, no matter how they're drawn, that have a basis number greater than 3?
That's what we're about to dive into next. We've got a whole list of usual suspect graphs and other intriguing examples that we put to the test.
Okay, you've definitely got my curiosity piqued. I'm ready to see what those examples reveal about the elusive world of basis numbers.
Let's dive in, but before we move on to part 2, I think it's worth taking a moment to really appreciate what we've covered so far. I agree. We've gone from the basics of planar and one planar graphs all the way to these incredibly specific subclasses and properties, like balanced orientations and skirt walks. My head is spinning, but in a good way.
I know what you mean. It's amazing how much complexity is hidden within these seemingly simple concepts.
Exactly. And the fact that there are still so many unanswered questions just makes it all the more intriguing.
Absolutely. And who knows, maybe one of our listeners will be the one to crack the code and discover the next breakthrough in this area.
That's a great thought. Okay, everyone take a deep breath, maybe grab a coffee or a snack.
Yeah.
And get ready for part 2. We'll be back soon to continue our exploration of one planar graphs and their basis numbers. Welcome back to the deep dive. I'm still reeling from all the fascinating details about one planar graphs we uncovered in part 1.
Right.
Are you ready to dive back in?
Absolutely. I think you'll find the examples we're going to discuss even more intriguing.
Okay.
But before we get to those, let's unpack another useful tool for analyzing one planar graphs, the auxiliary graph.
Ooh, a new tool. What exactly is this auxiliary graph and why do we need it?
It's especially helpful when we're dealing with one planar graphs that have disconnected skeletons.
Okay.
Remember, that means the uncrossed edges don't all form a single connected component.
Right, like separate islands of uncrossed edges within the overall graph.
Exactly. Now, the auxiliary graph, which we usually denote as Q,
Okay.
gives us a way to visualize how those islands are connected by the crossing edges.
Okay, so it's kind of like a map of the relationships between the different parts of the skeleton.
That's a great way to put it. Specifically, Q has a vertex for each connected component of the skeleton, and we add a double edge in Q for each pair of crossing edges in the original graph that connect vertices from the same two skeleton components.
Let me see if I'm following this correctly.
Yeah.
So if we have two crossing edges in our original graph that both connect vertices belonging to the same two skeleton components,
Right.
those two components will be represented by two vertices in Q with a double edge between them.
Precisely. The auxiliary graph helps us see the bigger picture of how those crossing edges are bridging the gaps between the different parts of the skeleton.
Okay, I'm starting to see how Q can be useful.
Yeah.
But how does it actually help us understand the basis number?
Well, there's a fascinating result that says if the auxiliary graph Q contains 3 edge disjoint spanning trees, then the original one planar graph has an 8 basis.
Whoa, hold on. An 8 basis? That seems like a huge jump from the 3 bases we were seeing earlier.
Right.
What's going on here?
It all comes down to how we can use those 3 spanning trees in Q to strategically divide the edges of the original graph into 2 subgraphs. Let's call them G1 and G2.
Right.
The goal is to make these subgraphs well-behaved in a certain sense.
Well-behaved meaning?
Meaning that their intersections should be connected, and each subgraph should have a connected skeleton. Remember how we said earlier that one planar graphs with connected skeletons have a basis number of at most 4? We're basically trying to create 2 such subgraphs.
Ah, I see. So we're partitioning the edges strategically to create these nice subgraphs that we already know how to handle.
You got it. Now here's the clever part.
Okay.
By excluding the edges corresponding to one of the spanning trees from each subgraph, we can ensure that the remaining edges form connected skeletons.
So each of those 3 standing trees acts as a sort of separator to help us create those connected skeletons in G1 and G2.
Precisely. And since each subgraph now has a connected skeleton, we know it has a 4 basis.
Right.
Then, because the intersection of the subgraphs is also connected, we can combine those 2 4 bases to get an 8 basis for the original graph.
Okay, that's pretty ingenious. It's like we're taking this complex one planar graph with a disconnected skeleton, breaking it down into manageable pieces using the auxiliary graph, and then putting the pieces back together in a clever way to get a handle on its basis number.
Exactly. It's a testament to the power of graph transformations and how they can reveal hidden structures and properties.
Absolutely. I remember we talked about the Desargues graph earlier, that non-toroidal graph that seemed like it might challenge our 3 basis findings. Does this auxiliary graph technique apply to the Desargues graph?
That's a great question. In one of its one planar drawings, the Desargues graph actually does have a disconnected skeleton. And if we construct its auxiliary graph, we discover that it contains 3 edge disjoint spanning trees.
So according to this result, the Desargues graph should have an 8 basis.
Right.
But didn't we already find a 3 basis for it earlier?
You have a sharp memory, and you've hit upon a crucial point. This result, using the auxiliary graph, provides an upper bound on the basis number. There might be other ways to construct a basis that uses even fewer cycles.
So the 8 basis is like a worst-case scenario.
Exactly. It gives us a guaranteed maximum, but the actual basis number could be smaller depending on the specific structure of the graph and how we choose our basis cycles.
Okay, that makes sense. Now I want to circle back to Poppy one-planar graphs and that concept of balanced orientation. We saw that if a Poppy one-planar graph has a balanced orientation of its skirt walks, we can guarantee a 3 basis.
Right.
But the big question is, can every Poppy one-planar graph be oriented in this balanced way?
That's the million-dollar question. And unfortunately, the answer isn't so simple. Let's take the Peterson graph as an example. Remember we mentioned earlier that in its typical Poppy one planar drawing, it doesn't have a balanced orientation.
Right, because of those interconnected skirt walks that create a kind of domino effect.
Exactly. In that specific drawing, we run into a problem because we can find a sequence of 5 skirt walks that are linked together. Each one sharing an edge with the next one. This forces us to orient 3 skirt walks of one crossing in the same direction, which violates the balanced orientation condition.
I see. So it's like a chain reaction where the orientation of one skirt walk dictates the orientation of its neighbor and so on. But does this mean that the Peterson graph can never have a balanced orientation no matter how we draw it?
That's a great question. And to be honest, it's still an open problem. It might be possible to find a different drawing of the Peterson graph where we can achieve a balanced orientation.
Okay.
But for that specific embedding, we're out of luck.
So the existence of a balanced orientation might depend on the specific way the graph is drawn.
Yeah.
That adds another layer of complexity.
Yeah.
But what about those near-independent skirt walks? You mentioned that those always lead to a balanced orientation.
Yes. That's one of the more satisfying results we have in this area.
Okay.
Remember, near-independent skirt walks mean that no two skirt walks from different crossings share two vertices. It's like saying, okay, skirt walks can be neighbors,
right,
but don't get too cozy with each other.
I like that. We're keeping those skirt walks at a safe distance to prevent any orientation conflicts.
Exactly. And if we can achieve that near independence, then we can always find a balanced orientation.
Okay.
Which in turn guarantees us that nice three basis.
So near independence is a kind of shortcut to a balanced orientation and a low basis number.
Yeah,
I love those kinds of elegant connections in math. But despite all these findings, we still haven't found a definitive answer to whether there exists a Poppy one-planar graph with a basis number greater than 3, right?
You're absolutely right. We've explored several specific examples and subclasses, and so far, nothing has broken that 3 basis barrier.
Okay.
But that doesn't mean those elusive graphs don't exist.
It's like a treasure hunt. We've got our map and our tools, but we're still searching for that hidden gem.
Right.
So where do we go from here? What other avenues can we explore in this quest for higher basis numbers?
Well, one thing we haven't touched upon yet is the computational side of things.
Okay.
Finding the basis number of a graph isn't as simple as plugging it into a formula.
Right.
It turns out to be a surprisingly complex problem from a computational perspective.
Wait, really? You mean there's no easy way to just calculate the basis number?
Unfortunately, no. In fact, for a general graph, we don't even know if there's an efficient algorithm to determine its basis number.
Right.
It might be what computer scientists call an NP-hard problem, meaning it's potentially very difficult to solve, especially as the graph gets larger.
Okay, so we're not just dealing with abstract math here.
Right.
We're bumping up against some fundamental limits of computation as well.
Exactly. And the complexity doesn't necessarily go away when we restrict ourselves to one-planar graphs.
Okay.
Even for this subclass, we don't have a clear understanding of how hard it is to compute the basis number, or even just to check if it's equal to 3.
So even though one-planar graphs seem close to planar graphs, in some ways, they still hold on to a lot of computational mysteries.
Absolutely. And that just highlights how much we still don't know about even these seemingly simple classes of graphs.
Right.
There's so much more to explore and discover.
This is blowing my mind. It's fascinating how something as seemingly basic as counting cycles can lead to these deep questions about the nature of graphs and the limits of computation.
I agree. It's one of the things that makes graph theory so captivating.
Yeah.
There's always another layer to peel back, another connection to uncover.
This deep dive has definitely given me a newfound appreciation for the complexity and the beauty hidden within these one-planar graphs.
Right.
I'm eager to see what other insights we can uncover in part 3.
I think you'll find it especially fascinating.
Okay.
We'll delve into some specific examples of one-planar graphs and see how all these concepts we've been discussing come to life in concrete cases.
I can't wait. So to everyone listening, take a moment to process all this incredible information.
Yeah.
And we'll be right back with the final part of this deep dive into the world of one-planar graphs. Welcome back to the deep dive. I'm ready to see these concrete examples you promised. After all the abstract concepts we've been discussing, I'm eager to ground ourselves in some actual graphs.
Absolutely. Let's start with a familiar face. The complete graph with 6 vertices, K6. Remember, it's the one where every vertex is connected to every other vertex.
Right, like a super-connected social network where everyone knows everyone else.
Yeah.
But we also mentioned that K6 isn't planar.
Yeah.
Meaning we can't draw it on a flat surface without any edges crossing.
Exactly. But it is one planar.
Okay.
We can draw it with, at most, one crossing per edge, which makes it a great example to analyze using the tools we've been discussing.
Okay, so K6 fits into our one-planar world. What about its basis number?
As we've seen earlier, K6 has a basis number of 3.
Right.
And we can actually construct a 3 basis for it by carefully choosing cycles that involve both the crossed and uncrossed edges.
So it's a balancing act between those two types of edges.
Right.
To make sure we can generate all possible cycles using only 3 basis cycles.
Exactly. Now, remember those special subclasses of one-planar graphs we talked about?
Right.
Well, K6 happens to tick a lot of those boxes.
Let's see. It's locally maximal, right? Because every crossing is part of a K4 subgraph.
You got it. And it also has a connected skeleton, meaning all the uncrossed edges form a single connected component. So K6 is a great example of a one-planar graph that exhibits a lot of the properties we've been discussing.
K6 is like the poster child for one-planar graphs.
Yeah.
Okay, what's next on our list of examples?
Let's move on to the complete bipartite graph with 3 vertices on one side and 4 on the other, K34.
Bipartite graph. Those are the ones with 2 groups.
Yeah.
And connections only exist between vertices from different groups, right?
Precisely. And K344 is another example of a one-planar graph with a basis number of 3.
Okay, so it's like a matchmaking graph, but with some crossed wires to make things interesting.
That's a fun way to visualize it. Now, K34 isn't locally maximal.
Okay.
Because not every crossing forms a K4 subgraph.
Right.
But it does have a connected skeleton.
So it shares some similarities with K6.
Yeah.
But it also has its own unique characteristics.
Yeah.
I'm starting to see how each of these examples gives us a slightly different perspective on the world of one-planar graphs.
Absolutely. Every graph tells a story. And by analyzing these specific examples, we start to uncover the patterns and connections that underlie the broader theory.
Okay, I'm ready for the next challenge. What other intriguing graph do you have in store for us?
Let's venture into the realm of higher dimensions with the 4-dimensional hypercube.
Ooh, hypercubes. I always find those a bit mind-bending.
I know what you mean. They can be tough to visualize, but they have fascinating properties.
Yeah.
Imagine starting with a regular 3-dimensional cube. Now, instead of squares as faces,
Right.
imagine it has cubes as faces.
Okay.
That's the basic idea behind a 4-dimensional hypercube.
Okay, I'm trying to picture it. It's like a cube within a cube.
You're on the right track. It's
Yeah.
definitely a challenge to wrap our 3-dimensional minds around it.
Right.
But the key is to think about how the connections between the vertices extend into that 4th dimension.
So how does this 4-dimensional hypercube fit into the world of one-planar graphs?
Well, believe it or not, it is one-planar. We can actually represent it in a way that satisfies the one crossing per edge rule. And just like our previous examples, it also has a basis number of 3.
Wow, it's amazing. So we can find the 3 bases even in this mind-boggling multi-dimensional structure.
Exactly. And it also has a connected skeleton.
Okay.
But it's not locally maximal since it doesn't contain any K4 subgraphs.
Okay, so the 4-dimensional hypercube is another example of a one-planar graph that fits into some of our subclasses, but not others.
Right.
It's fascinating to see how these concepts play out in such diverse graphs.
It really highlights the breadth and depth of graph theory, doesn't it? Even when we focus on a specific class like one-planar graphs, we encounter such a wide range of structures and properties.
Absolutely. Okay.
Yeah.
Ready for some more visual inspiration. What about those beautiful graphs we mentioned earlier?
Yeah.
The Peterson graph and the Hewood graph.
Yes. Those are classics for a reason.
Yeah.
They're known for their elegant symmetry and intricate structures.
I've seen pictures of them before, and they really do look like works of art.
They are. And both the Peterson graph and the Hewood graph are one-planar with a basis number of 3.
So their beauty is not just skin deep. It extends to their cycle structure as well.
Yeah.
Are there any other interesting features they exhibit in terms of our one-planar subclasses?
In their typical one-planar drawings, the Peterson graph doesn't have a connected skeleton,
Okay.
while the Hewood graph does.
So once again, we see a mix and match of properties. It's like each graph has its own unique personality based on these different characteristics.
Exactly, and that's what makes analyzing these examples so rewarding.
Right.
We start to see the nuances and the connections that might not be obvious just from looking at the abstract definitions.
Okay, you mentioned one more graph earlier, the McGee graph.
Right.
What's special about this one?
The McGee graph is a cubic graph, meaning each vertex has degree 3,
Okay.
and it's also one planar with a basis number of 3.
Cubic graphs, I remember those.
Yeah.
Each vertex is like a perfectly balanced 3-way intersection.
Precisely.
Yeah.
Now, the McGee graph, in its typical one-planar drawing, doesn't have a connected skeleton.
Okay.
And it's not locally maximal either.
So it's a bit of a loner in the one-planar world with its own set of distinct features.
You could say that. It just goes to show that even within a seemingly specific category like one-planar graphs, there's still a remarkable amount of diversity.
This whole deep dive has been a whirlwind tour through the world of one-planar graphs.
Good.
I'm honestly amazed by how much we've uncovered.
Me too. We've gone from the basic definitions to exploring intricate subclasses, understanding the significance of basis numbers, and even touching upon the computational challenges involved.
I feel like I've gained a whole new appreciation for the complexity and the beauty of these graphs.
I hope so. And remember, this is just the tip of the iceberg.
Right.
There's so much more to explore in the world of graph theory, and we've only scratched the surface of what's out there.
That's both exciting and a little bit daunting. But I definitely feel inspired to keep learning and exploring.
Great.
Thank you for guiding us through this fascinating landscape.
It's been my pleasure. And to everyone listening, I encourage you to continue your own exploration of graph theory.
Yeah.
Who knows, maybe you'll be the one to solve some of the open problems we've discussed.
Right.
Or discover entirely new and amazing properties of these fascinating structures.
That's a great thought. And on that note, we've reached the end of our deep dive into the world of one-planar graphs and their basis numbers.
Thank you for joining us on this journey, and we hope you'll tune in for our next deep dive into the fascinating world of mathematics.
Until next time, keep those math neurons firing. Welcome to the deep dive. Today we're going deep into the world of one-planar graphs and their basis numbers.
Oh, cool.
Specifically, we'll be exploring this research paper titled The Basis Number of One-Planar Graphs.
Sounds interesting.
Yeah, it's a fascinating look at graphs that can be drawn in the plane with at most one crossing per edge.
It really is. You see, one-planar graphs occupy this interesting space between planar graphs, which we can draw without any crossings,
Right.
and more general graph structures where crossings can be more rampant. This paper tackles the question, what is the basis number of these almost planar graphs?
Right. Now, I remember from graph theory that McLean's planarity criterion tells us a graph is planar if and only if it has a 2 basis.
Yes.
But to really understand what's going on here, we need to delve into the concept of cycle spaces.
Absolutely. Let's start with the basics. The cycle space of a graph, denoted as CG, is the set of all its Eulerian subgraphs.
Right.
Remember, an Eulerian subgraph is one where every vertex has an even degree. Think of it like those puzzles where you try to trace a path without lifting your pen, covering each edge exactly once.
Ah, yes, the classic Bridges of Königsberg problem.
Yes.
So how does this set of Eulerian subgraphs form a vector space?
It's a bit surprising at first, but it all comes down to how we define addition and scalar multiplication. The vector space is over the field F2, meaning we're working with 0 and 1. Our vectors are the Eulerian subgraphs themselves, and the addition operation is the symmetric difference. You take two subgraphs, and their sum, or symmetric difference, is a new subgraph containing only those edges present in one subgraph but not the other.
So it's like a canceling out effect.
Right.
If an edge appears in both subgraphs, it disappears in the sum.
Precisely. Scalar multiplication is straightforward in this case.
Yeah.
Multiplying a subgraph by 1 gives you the same subgraph, and multiplying by 0 gives you the 0 vector, which is the empty subgraph.
Okay, so we've got our vector space of Eulerian subgraphs.
Yes.
Now, what about generating sets and basis?
A generating set for CG is a collection of Eulerian subgraphs that can be combined using symmetric difference to create any other Eulerian subgraph in the space.
Right.
Imagine having a toolbox of these special subgraphs. You can combine them to build any possible closed path in your graph.
And a basis is like a minimal generating set.
Exactly.
The most efficient toolbox possible with no redundant tools.
Now, remember that McLean's criterion mentioned a 2 basis.
Yeah.
The 2 here refers to the concept of charge.
Okay.
The K basis for CG is a basis where every edge of the graph is contained in at most K cycles of the basis.
Right.
The basis number of a graph is the smallest K for which G has a K basis.
So for planar graphs, we know the basis number is at most 2.
Yes.
This paper delves into the basis number of one planar graphs.
Right.
It seems intuitive that allowing one crossing per edge wouldn't drastically change things, right?
That's what you might think, yes.
Maybe the basis number would be 3 at most.
That's what one might expect. But as we'll see, one planar graphs can be surprisingly complex when it comes to their cycle spaces.
Oh.
The paper actually shows that the basis number of one planar graphs can be unbounded.
Unbounded. So even with just one crossing per edge, things can get really wild.
Indeed. The authors construct a family of one planar graphs with increasingly large basis numbers, proving that there's no upper limit. It's pretty counterintuitive.
Okay, I'm definitely intrigued now. Can you walk us through this construction? Sure. How do they create these one-planar graphs with such large basis numbers?
It all starts with an arbitrary graph, G, that has a known high basis number.
Okay.
This initial graph might not be one-planar.
Right.
It could have vertices of high degree and multiple crossings per edge.
So they start with a graph that's already a bit of a rebel in terms of its basis number.
Exactly. The key is to modify this graph in a way that makes it one-planar while preserving its high basis number.
Right.
They achieve this through a two-step process.
Okay, what's the first step?
The first step addresses those high-degree vertices.
Okay.
For any vertex with a degree greater than 3, they split it into 2 vertices connected by a new edge.
Okay.
They distribute the original vertex's neighbors among these 2 new vertices.
Right.
This process is repeated until all vertices have a degree of at most 3.
It's like surgically reducing the complexity of those high-degree vertices.
Yes.
While maintaining their overall connectivity.
That's a great way to put it. And importantly, this step doesn't decrease the basis number.
Okay.
Lemma 3.1 in the paper establishes that contracting an edge can never increase the basis number.
So if we could reverse this splitting process by contracting those newly added edges, we'd end up back at the original graph with its high basis number.
Precisely. Now, the second step tackles the issue of multiple crossings per edge.
Okay.
They draw this modified graph in the plane, allowing for crossings, and then subdivide each edge that has multiple crossings.
Subdivide, you mean adding new vertices along the edges?
Exactly. They insert these subdivision vertices between consecutive crossings on an edge.
So it's like they're smoothing out those multiple crossings by breaking them down into a series of single crossings.
Yeah.
Effectively turning the graph into a neatly organized one-planar graph.
That's a great analogy. And crucially, subdividing an edge doesn't change the basis number at all, as shown in Lemma 3.6.
So even though we've simplified the drawing and constrained the degrees, we haven't actually reduced the complexity of the cycle space.
Exactly. We can still obtain the original graph with its high basis number by contracting those subdivided edges.
Okay.
This implies that our modified one-planar graph must have a basis number at least as large as the original graph's basis number.
Okay, so we've taken a graph with a high basis number, made it one-planar without reducing that number, and now we have a family of such graphs.
Right.
How does this prove that the basis number of one-planar graphs can be unbounded?
Remember that we started with an arbitrary graph G with a known high basis number. We can repeat this construction process for graphs with increasingly larger basis numbers.
Okay.
Since the basis number of the resulting one-planar graphs is at least as large as the starting graph's basis number, we can create one-planar graphs with arbitrarily large basis numbers. This means there's no fixed upper limit, so the basis number of one-planar graphs is unbounded.
That's a pretty ingenious construction. It really highlights that even with seemingly simple constraints like allowing only one crossing per edge, the cycle space can still be incredibly complex. It makes you wonder, are there any subclasses of one-planar graphs where things are more well-behaved?
Yes. The paper delves into several subclasses where the basis number is bounded.
Okay.
These include graphs with connected skeletons, locally maximal one-planar graphs, poppy one-planar graphs, and optimal one-planar graphs.
Okay, we've got a lot to unpack there.
Yes, we do.
Before we move on to these specific subclasses, let's take a moment to clarify what we mean by the skeleton of a one-planar graph. It sounds a bit spooky.
Not spooky at all. The skeleton of a one-plane graph is simply the subgraph formed by all the uncrossed edges.
Oh.
Imagine you have your one-planar drawing and you erase all the edges that have a crossing.
Okay.
What's left is the skeleton.
There's like the underlying framework of the graph without those pesky crossing edges?
Exactly.
Right.
And it turns out that the connectedness of the skeleton plays a key role in bounding the basis number.
Okay, I'm ready to dive into these subclasses and see how this connected skeleton idea comes into play. All right, well, let's unpack these subclasses of one-planar graphs where the basis number is bounded.
Okay.
You mentioned graphs with connected skeletons.
Yeah.
What makes them so special?
The key insight here is that if the skeleton of a one-planar graph is connected, we can cleverly decompose the graph into 2 planar subgraphs.
Hold on.
Yeah.
How do we get 2 planar graphs from a single one-planar graph?
It's a neat trick. Take your one-planar graph and identify all the pairs of edges that cross. Now, create 2 new graphs. The first graph includes all the edges of the skeleton, plus 1 edge from each crossing pair.
Right.
The second graph also includes all the edges of the skeleton, but includes the other edge from each crossing pair.
Ah, so we're essentially splitting those crossing edges between 2 graphs. ensuring that neither graph has any crossings within itself.
Exactly. Since each new graph only contains one edge from each crossing pair, both become planar.
Right.
Now remember, Lemma 3.8 from the paper.
Refresh my memory.
Lemma 3.8 states that if we can cover a graph with two subgraphs whose intersection contains a spanning tree and is connected,
right,
then the basis number of the original graph is at most the sum of the basis numbers of those two subgraphs.
Okay, I see where this is going.
Yeah.
Our two planar subgraphs cover all the edges of the original one planar graph.
Right.
And their intersection is precisely the connected skeleton.
Yes.
Which definitely contains a spanning tree.
You got it.
Yeah.
And since planar graphs have a basis number of at most 2, the basis number of our original one planar graph with a connected skeleton is at most 4.
Wow, that's a really elegant application of planar graph properties to bound the basis number of a more complex graph.
It is. This technique highlights how understanding simpler structures can help us unlock the secrets of more intricate ones.
Okay, connected skeletons check. What about locally maximal one planar graphs? What makes them special?
A locally maximal one planar graph is one where you can't add any more edges without violating the one planarity condition.
Right.
More specifically, for every pair of edges that cross, the 4 endpoints of those edges must form a complete graph, K4.
So we're essentially forcing a lot of interconnectedness around those crossing points.
Precisely. And importantly, as Lemma 4.3 shows,
right,
locally maximal one planar graphs can always be redrawn so that their skeletons are connected.
Ah, so by forcing those K4 structures around each crossing, we indirectly ensure a connected skeleton.
Right.
Which in turn bounds the basis number to at most 4. It's all starting to connect now.
Exactly. It's fascinating how different structural properties can influence each other in sometimes unexpected ways.
Now, on to Poppy one planar graphs.
Right.
What's the story with those?
Poppy one planar graphs get their name from a particular structure that arises around each crossing.
Okay.
Imagine a crossing point and the 4 edges involved in that crossing.
Okay.
The poppy consists of those 4 edges,
right,
plus all the cycles in the skeleton that surround the crossing and connect the endpoints of those crossing edges.
So it's like a little flower blooming around each crossing point.
A very poetic way to put it, the crucial property of a poppy is that the union of these surrounding cycles forms a simple cycle in the skeleton.
Yeah.
Meaning it doesn't cross itself.
Okay, I'm picturing these poppies now.
Yeah.
But how do they help us bound the basis number?
Well, just like the maximal one planar graphs, poppy one planar graphs also have connected skeletons, as stated in Lemma 4.3.
Okay.
And as we've already seen, a connected skeleton implies a basis number of at most 4.
So those poppies, despite their whimsical name,
right,
pack a punch when it comes to controlling the complexity of the cycle space.
They do. Now, the paper delves even deeper into Poppy 1 planar graphs, exploring whether we can tighten that bound from 4 down to 3.
Ooh, that sounds interesting.
Yeah.
What's the key to achieving this tighter bound?
The key lies in finding a balanced orientation of what are called the skirt walks in the skeleton.
Hold on, rewind a bit.
Okay.
What are skirt walks again?
The skirt walks are the paths in the skeleton that screte around a crossing point, connecting the endpoints of the crossed edges.
Okay.
So for each crossing, there are 4 skirt walks, one for each segment of the cycle surrounding that crossing.
Okay, got it.
Yeah.
And what does it mean for these skirt walks to have a balanced orientation?
Similar to the balanced orientation we discussed earlier for the cycles surrounding crossings,
right,
we want to orient the edges of the skeleton so that for each crossing, 2 of the 4 skirt walks are oriented clockwise, and 2 are oriented counterclockwise.
So we're essentially trying to balance the directional flow of those skirt walks around each crossing point.
Yeah.
But why is this balanced orientation so important for getting a 3 basis?
It allows us to apply a clever construction technique.
Okay.
We can assign the values 1 and 2 to the skirt walks based on their orientation.
Okay.
Then we can choose specific bases for the K4 poppies that respect those assignments.
Right.
The balance orientation ensures that the charges on the edges stay low.
Okay.
If we combine these carefully chosen K4 poppy bases with the face boundaries of the skeleton, excluding the cycles around the crossings, we end up with a 3 basis for the entire Poppy 1 planar graph.
Wow, that's amazing. So finding this balanced orientation is crucial for achieving that tighter bound.
Yeah.
But isn't finding such an orientation tricky?
It can be, yes.
What if a Poppy 1 planar graph doesn't have one?
You're sharp. Finding a balanced orientation can indeed be challenging, and not all Poppy 1 planar graphs have one. The paper actually shows that the Peterson graph, a classic non-planar graph,
Right.
doesn't admit a balanced orientation in its Poppy 1 planar drawing.
So a 3 basis for general Poppy 1 planar graphs is only guaranteed if this balanced orientation exists.
Exactly. Theorem 4.16 formalizes this result.
Okay.
The existence of a 3 basis for all Poppy 1 planar graphs, regardless of whether they have a balanced orientation, remains an open question.
That's a pretty fascinating open question.
It is.
I'm curious.
Yeah.
Are there any special cases of Poppy 1 planar graphs beyond those with a guaranteed balanced orientation?
Yes.
Where we do know a 3 basis exists?
Yes. The paper highlights a class of Poppy 1 planar graphs called near-independent skirt-walk graphs, as defined in definition 4.17.
Okay.
In these graphs, no two skirt walks of different crossings share two vertices.
So they keep those skirt walks relatively separated.
Precisely.
Preventing too much overlap.
This separation property allows us to orient the skirt walks of each Poppy independently without worrying about conflicts. Theorem 4.18 confirms that Poppy 1 planar graphs with near-independent skirt walks always have a balanced orientation and therefore a 3 basis.
It's amazing how this seemingly simple condition of keeping the skirt walks separated has such profound implications on the basis number.
It really highlights the intricate relationship between graph structure and the complexity of the cycle space. Now, before we wrap up our discussion on one-planar graphs,
Okay.
I'd like to touch upon another subclass mentioned earlier, optimal one-planar graphs.
Okay.
These are simple one-planar graphs with the maximum possible number of edges for a given number of vertices.
Right.
That number happens to be 4 and 8, where n is the number of vertices.
So they're packing in as many edges as they can while still remaining one planar.
Exactly.
What's their connection to basis numbers?
It turns out that optimal one-planar graphs fall under the umbrella of full-crossing one-planar graphs.
Okay.
A full-crossing one-planar graph is one where every crossing is surrounded by a K4,
Right.
not just induced by the endpoints of the crossing edges.
Right.
This restrictive drawing condition leads to some elegant properties that help us establish a tight bound on their basis number.
Okay, I'm sensing that full crossing graphs are a key piece of the puzzle here.
They are.
Let's dive into them and see what secrets they hold. Okay, full crossing one planar graphs.
Yeah.
Every crossing surrounded by a K4.
Right.
Sounds like this really tightens up the structure.
Yes, it does.
How does that help us with the basis number?
It leads to a very specific way to construct a generating set for the entire cycle space.
Okay.
Remember those fundamental cycles we talked about earlier?
Uh-huh.
The ones you get by adding an edge to a spanning tree?
Ah, yes. Those cycles formed by the tree edges and a single non-tree edge.
Well, if we choose a spanning tree of the skeleton,
Okay.
this set of fundamental cycles corresponding to the non-tree edges of the skeleton forms a basis.
Right.
And therefore a generating set for the cycle space of the skeleton.
Okay, that makes sense.
Yeah.
So we have a generating set for the skeleton.
Yes.
How do we incorporate those K4 structures around each crossing?
Here's where lemma 4.8 comes in.
Okay.
It tells us that we can create a generating set for the entire full crossing one plane graph
Right.
by taking the generating set for the skeleton
Right.
and making a clever modification around those crossings.
Okay.
Specifically for each K4 poppy,
Yeah.
we remove the cycle in the skeleton that surrounds the crossing
Right.
and add a basis for the K4 itself.
So we're swapping out those skeleton cycles for a set of carefully chosen cycles within the K4s.
Exactly.
But why does this new set generate the entire cycle space of the full crossing graph?
The proof hinges on the fact that any cycle in the full crossing graph can be broken down into segments
Okay.
that either lie entirely within the skeleton or entirely within a K4 poppy.
Okay.
Since we have generating sets for both the skeleton and each K4, we can build up any cycle we want.
Okay, I see the logic.
Yeah.
But how do we ensure that the charges stay low? Remember, we're aiming for a 3 basis.
That's where things get really clever. Lemma 4.9 tells us that for each K4 poppy,
Okay.
we can choose a basis with some very specific properties.
Right.
If we assign the values 1, 1, 2, and 2 to the 4 edges of the cycle in the skeleton that surrounds the crossing, we can find a basis for the K4 such that the charge of each edge in the surrounding cycle is at most its assigned value,
Right.
and the charges of the other 2 edges of the K4 are at most 3.
Hold on. How do we decide which edges of the surrounding cycle get the 1s and which get the 2s?
Yeah.
It seems kind of arbitrary.
It's not arbitrary at all. That's where lemma 4.10 steps in.
Okay.
It states that we can orient the edges of the skeleton
Mm-hmm.
in such a way that for each of those surrounding cycles, exactly 2 edges are oriented clockwise and 2 are oriented counterclockwise.
So we use this orientation to guide our assignment of 1s and 2s.
Right.
Edges oriented in one direction get the 1s, and those oriented in the other get the 2s.
Yeah.
But how do we even find such a magical orientation?
It involves the dual graph of the skeleton.
Okay.
Picture placing a vertex in each face of the skeleton and connecting two vertices if their corresponding faces share an edge.
Okay, I'm picturing it.
Yeah.
We're essentially flipping the roles of faces and vertices.
Exactly. Now, there's a classic result that says we can orient the edges of any graph, including this dual graph,
right,
in such a way that each vertex has at most half its edges pointing inwards and at most half its edges pointing outwards.
It's like balancing the flow of those arrows around each vertex.
Right. We find such a balanced orientation for the dual graph.
Right.
And then here's the trick.
Yeah.
For each edge in the original skeleton, we orient it to cross the corresponding edge in the dual graph from left to right.
Interesting. So the orientation of the dual graph induces an orientation on the original skeleton.
Exactly.
And since the dual graph's orientation was balanced,
yes,
this induced orientation on the skeleton will also be balanced in the sense we need...
Precisely. We can now use this balanced orientation to assign those 1s and 2s to the edges of the cycle surrounding the crossings.
Okay.
Now, with all these pieces in place, Theorem 4.11 puts it all together.
Okay, let's hear it.
The theorem states that if we take all those carefully chosen bases for the K4 poppies with their charge assignments based on the balanced orientation and combine them with the face boundaries of the skeleton, excluding those surrounding cycles, we get a 3 basis for the entire full crossing one-plane graph.
Whoa, a 3 basis?
Check.
So all that intricate construction work pays off in the end.
Exactly. Think about the charge of an edge in this final 3 basis.
Okay.
If the edge is crossed, it's part of a K4 poppy, and its charge is at most 3 because it's only used in that poppy's basis.
Okay.
If the edge is uncrossed, it's part of 2 face boundaries in the skeleton.
Right.
And because of our clever orientation and 1s and 2s assignments, the charges from those 2 face boundaries add up to at most 3.
So it all beautifully balances out to ensure no edge gets overloaded.
Right.
Now, you mentioned that optimal one-planar graphs are a special case of full crossing graphs.
Yes.
Does this mean they also have a 3 basis?
Yes. Corollary 4.12 confirms that optimal one-planar graphs, being full crossing, also have a basis number of 3.
It's fascinating how this maximal edge property indirectly leads to a more constrained cycle space.
It really highlights the interconnectedness of these graph properties.
I remember we talked about poppy one-planar graphs in general.
Yes.
For those that don't have a balanced orientation of their skirt walks.
Right.
Is there any hope of finding a 3 basis?
That's a great question, and unfortunately the paper doesn't provide a definitive answer.
Okay.
The existence of a 3 basis for all poppy one-planar graphs, regardless of balanced orientation, is left as an open problem.
Okay, so that's one for the graph theory community to ponder. We've explored so much about one-planar graphs and their basis numbers.
We have.
From the surprising result that the basis number can be unbounded, to the elegant constructions involving connected skeletons, K4 poppies, balanced orientations, and those intriguing open problems. This deep dive has been quite a journey. What are your final thoughts on this area of research?
Well, I think it's amazing how even a slight relaxation of planarity, like allowing just one crossing per edge, can lead to such a dramatic increase in the complexity of the cycle space.
Yeah.
It really underscores how delicate the balance between structure and complexity is in graph theory.
It also makes you appreciate the power of those special subclasses where we contain that complexity and find those nice bounds on the basis number.
Absolutely. Those subclasses highlight how certain structural properties can act as constraints, bringing order to what might otherwise be a chaotic landscape.
This paper has certainly given us a lot to think about. I'm sure our listeners will be pondering those open problems and exploring the intricate world of one-planar graphs for quite some time.
I hope so. It's a fascinating area with plenty of room for further discovery.
And that brings us to the end of our deep dive. Thanks for joining us on this mathematical adventure, and we'll see you next time on the Deep Dive.